3 million light-years away, a galaxy spins so fast it should tear itself apart. The Triangulum Galaxy harbors star nurseries that birth suns 100 times more massive than ours. We'll witness blue giants that burn through their fuel in mere millions of years, explore pink nebulae where stars are dying in cosmic cocoons, and discover rogue black holes wandering through spiral arms like cosmic predators. Prepare yourselves. We begin. The Triangulum Galaxy spins like a cosmic hurricane that should have destroyed itself billions of years ago. Every night, astronomers point their telescopes toward the constellation Triangulum and witness something impossible. This spiral galaxy, officially catalogued as Messier 33, rotates at speeds that violate everything we know about orbital mechanics. The outer regions move so fast, they should fling themselves into the void like water droplets flying off a spinning wheel. Yet here it stands, defiant. The galaxy stretches 60,000 light-years across, containing 40 billion stars arranged in perfect spiral arms. These arms sweep through space in an elegant dance, but the physics behind this dance makes no sense. According to Newton's laws, objects farther from the center should move slower, just like planets in our solar system. Mercury races around the sun while distant Neptune crawls along its orbit, but Triangulum breaks these rules. Stars at the galaxy's edge move just as fast as those closer to the center. Some regions even accelerate as they get farther out. It's like watching a merry-go-round where the horses on the outer rim gallop faster than those near the center. The centrifugal force should tear the galaxy apart, scattering its stars across the cosmos like cosmic shrapnel. The mystery deepens when we measure the galaxy's mass. All the visible matter, every star and gas cloud we can detect, accounts for only 10% of the gravitational pull needed to hold this spinning monster together. The remaining 90% comes from something invisible, something that doesn't interact with light or ordinary matter. We call it dark matter. This ghostly substance forms an invisible scaffolding around the galaxy, its gravitational grip preventing the spiral arms from flying apart. Dark matter outweighs all the visible stars 5 to 1, yet we can only detect it through its gravitational effects. It's like trying to understand a dance by watching the shadows on the wall. The implications stagger the mind. If dark matter exists throughout the universe, then everything we see, every star and planet and galaxy, represents just a tiny fraction of reality. We're like inhabitants of a vast city who can only see the streetlights, unaware of the massive buildings that surround us. The Triangulum Galaxy has been spinning this impossible dance for over 10 billion years. Generation after generation of stars have lived and died while this cosmic puzzle has remained unsolved. Each rotation takes 200 million years to complete, and in that time, countless civilizations could have risen and fallen on worlds orbiting its 40 billion suns. But this spinning mystery is just the beginning of our journey. Deep within those spiral arms, something even more extraordinary awaits us. Deep within the Triangulum Galaxy's spiral arms, cosmic nurseries are giving birth to monsters. The largest star-forming region in the galaxy, known as NGC 604, glows with the intensity of 600,000 suns. This stellar maternity ward spans over 1,000 light-years, making it 40 times larger than the Orion Nebula that decorates our night sky. Within this churning cauldron of gas and dust, gravitational forces are sculpting stars, so massive they dwarf our sun like mountains dwarf pebbles. The process begins in silence and darkness. Vast clouds of hydrogen gas, each containing enough material to build 1 million solar systems, drift through space at temperatures just above absolute zero. These molecular clouds are the raw materials of creation, invisible to our eyes but dense enough to block the light of background stars. Then something triggers the collapse. Perhaps a nearby supernova sends shockwaves rippling through the cloud, or maybe 2 gas clouds collide in a cosmic traffic accident. Whatever the cause, gravity takes hold with crushing inevitability. The cloud begins to contract, slowly at first, then faster as its own gravity strengthens. What started as a gentle drift becomes a headlong plunge toward the center. As the gas compresses, it heats up like air in a bicycle pump. The temperature climbs from near absolute zero to thousands of degrees. The cloud fragments into smaller pockets, each destined to become a star. But in the dense heart of NGC 604, some fragments gather so much material they become true giants. These stellar behemoths contain 50, 70, even 100 times more mass than our Sun. They burn with temperatures exceeding 40,000 degrees, making them 50,000 times brighter than the star that warms our Earth. Their surfaces glow brilliant blue-white, so hot they ionize the surrounding gas and paint the nebula in shades of electric pink and turquoise. The most massive stars in Triangulum are living on borrowed time. While our Sun will burn steadily for 10 billion years, these giants exhaust their nuclear fuel in just a few million years. They're like cosmic Roman candles, burning brilliantly but briefly before exploding in spectacular supernovas that can outshine entire galaxies. The irony is profound. The most massive stars, the ones that seem most powerful and enduring, are actually the most fragile. They burn through their hydrogen fuel so quickly that they barely have time to develop planetary systems before they die. Any worlds that might form around these giants would be sterilized by radiation long before life could take hold. Yet their deaths are not meaningless. When these giants explode, they forge heavy elements in their cores and scatter them across the galaxy. The calcium in our bones, the iron in our blood, the oxygen we breathe, all were forged in the nuclear furnaces of dying stars. But even these stellar giants pale in comparison to the dark predators that hunt between the spiral arms. Between the glowing spiral arms of Triangulum, invisible hunters drift through the darkness like cosmic sharks. These rogue black holes were born from the deaths of the most massive stars, but unlike their siblings that remain anchored in binary systems, these wanderers have been kicked out of their birthplaces. The violent asymmetry of their formation, when a star's core collapsed in an uneven supernova explosion, sent them careening through space at speeds reaching thousands of kilometers per second. Now they roam the galaxy alone, each one a gravitational monster with the mass of dozens of suns compressed into a sphere smaller than a city. They're completely invisible, detectable only when they devour something in their path. Most of the time they glide through the near vacuum of interstellar space, as silent and deadly as submarines in the deep ocean. The Triangulum Galaxy likely harbors millions of these stellar mass black holes, the graveyard remnants of ancient star-forming epochs. Some formed when the galaxy was young and metal-poor, creating black holes with different properties than those born today. Others are refugees from galactic mergers, flung into wandering orbits when their host galaxies were torn apart by tidal forces. When a rogue black hole encounters a star, the results can be catastrophic. The black hole's gravity creates tidal forces that stretch and squeeze the star like a cosmic stress ball. If the star ventures too close, it crosses the event horizon and vanishes forever, adding its mass to the black hole's growing bulk. But if it maintains just the right distance, the black hole strips away the star's outer layers in a process called tidal disruption. These stellar cannibalization events create some of the most energetic phenomena in the universe. As the torn matter spirals into the black hole, it forms an accretion disk that glows with temperatures exceeding millions of degrees. The disk launches jets of plasma at nearly the speed of light, creating beacons that can be seen from billions of light years away. The most dangerous rogues are the ones we can't see coming. Unlike active black holes, surrounded by glowing accretion disks, a solitary wanderer produces no light signature. It's like trying to spot a black cat in a coal mine. The only warning would come from gravitational lensing, the way the black hole's gravity bends the light of background stars like a cosmic magnifying glass. For any planetary system in the path of a rogue black hole, the encounter would be apocalyptic. The black hole wouldn't need to directly hit a planet to destroy it. Its gravity would disrupt planetary orbits, potentially flinging worlds into interstellar space, or sending them crashing into their parent stars. The tidal forces alone could trigger massive earthquakes and volcanic eruptions that would reshape entire worlds. The most chilling aspect of these cosmic predators is their longevity. While stars burn out and galaxies evolve, black holes persist virtually forever. They'll still be wandering the cosmos long after the last star has died and the universe has grown cold and dark. In the far future, they may be the only active players in a dead universe, occasionally finding each other in the darkness and merging in collisions that shake the fabric of space-time itself. But not all of Triangulum's wonders are hidden in darkness. In the galaxy's star-forming regions, celestial artists are painting masterpieces in light. Scattered throughout Triangulum's spiral arms, delicate pink veils mark the final breath of dying stars. These glowing clouds, called planetary nebulae, have nothing to do with planets. The name came from 18th century astronomers who thought they looked like distant worlds through their primitive telescopes. In reality, each nebula is a stellar death shroud, the outer layers of a sun-like star blown into space during its final moments. The process begins when a star exhausts the nuclear fuel in its core. For billions of years, the star has maintained a delicate balance between the inward pull of gravity and the outward pressure of nuclear fusion. But when the fuel runs out, gravity wins. The core collapses and heats up, while the star's outer layers expand and cool, transforming the once stable star into a bloated red giant. As the red giant phase continues, the star becomes increasingly unstable. Thermal pulses deep in its core send shock waves rippling through the stellar atmosphere. These pulses blow off the star's outer layers in a series of gentle puffs, like cosmic smoke rings expanding into space. The ejected material forms a hollow shell around the dying star, initially invisible in the cold darkness. Then comes the transformation that creates the beauty we see. The star's core, now exposed as a white dwarf, burns at temperatures exceeding 100,000 degrees. This stellar ember floods the expanding shell with ultraviolet radiation so intense it strips electrons from atoms in the surrounding gas. The ionized hydrogen glows red while oxygen emits green and blue light. The result is a cosmic stained glass window painted in impossible colors. Each planetary nebula tells a unique story of stellar death. Some form perfect spheres, their gas expanding uniformly in all directions. Others create intricate patterns, hourglass shapes, or butterfly wings, sculpted by magnetic fields and companion stars. The most complex nebulae resemble cosmic flowers, with delicate petals of glowing gas arranged in symmetrical patterns that rival any artwork created by human hands. The timescales involved are both vast and fleeting. The dying star took billions of years to reach this point, burning steadily through most of the universe's history. But the planetary nebula phase lasts only tens of thousands of years, a cosmic blink of an eye. The expanding shell gradually disperses into the interstellar medium, enriching the galaxy with heavy elements forged in the star's core. These elements become the building blocks for future generations of stars and planets. The carbon in our DNA, the nitrogen in our atmosphere, the phosphorus in our bones, all were created in the nuclear furnaces of dying stars and distributed through planetary nebulae. We are literally made of star stuff, recycled cosmic material that once glowed in nebulae like these. The white dwarf at the nebula's center will continue to shine for trillions of years, slowly cooling from white-hot to red to brown to black. It's a preview of our own sun's fate, destined to follow the same path when it exhausts its fuel 5 billion years from now. Our sun will swell into a red giant, engulf the inner planets, and then cast off its outer layers in a final act of cosmic artistry. But while some stars die with gentle beauty, others choose a more violent end, one that can outshine entire galaxies in a single moment of stellar rage. In the heart of Triangulum's most active star-forming regions, blue supergiants burn like cosmic torches, racing toward their own destruction. These stellar giants represent the ultimate paradox of stellar evolution. They're the most massive, most luminous, and most spectacular stars in the galaxy, yet they live the shortest lives. A blue supergiant burns through its nuclear fuel like a Formula One car burning rubber, converting 4 million tons of matter into energy every second. The nuclear furnace in its core reaches temperatures of 50 million degrees, hot enough to fuse elements all the way up to iron. The star's surface temperature exceeds 40,000 degrees, nearly 7 times hotter than our sun. This extreme heat gives the star its characteristic blue-white color and makes it shine with the brightness of 100,000 suns. The stellar wind it produces is so powerful, it strips away material at rates that would completely evaporate our sun in just a few million years. These giants are essentially living on borrowed time from the moment they ignite. While our sun will burn steadily for 10 billion years, a blue supergiant exhausts its hydrogen fuel in just 3 to 5 million years. It's like comparing a sip of water to a fire hose, both drawn from the same reservoir but consumed at vastly different rates. The star's death throes begin in its core, where nuclear fusion has built up layers of increasingly heavy elements. Hydrogen fuses to helium, helium to carbon, carbon to oxygen, oxygen to silicon, and finally silicon to iron. Each fusion stage releases less energy than the previous one, like a fire burning through progressively damper wood. When the core starts producing iron, the star's fate is sealed. Iron cannot fuse to release energy. It can only absorb it. The nuclear furnace that has supported the star for millions of years suddenly becomes an energy sink. The core temperature plummets, and with it, the outward pressure that has held the star together against its own gravity. What happens next occurs faster than a human heartbeat. The core collapses from the size of Earth to the size of a city in less than a second. The density becomes so extreme that protons and electrons are crushed together to form neutrons. The collapsing matter rebounds off this neutron core like a rubber ball hitting concrete, creating a shock wave that rips through the star's outer layers. The explosion that follows can outshine an entire galaxy. In a matter of seconds, the supernova releases more energy than our sun will produce in its entire 10 billion year lifetime. The blast wave expands at speeds of 30,000 kilometers per second, heating the surrounding gas to temperatures exceeding 1 billion degrees. The supernova enriches the galaxy, with heavy elements forged in the star's core and during the explosion itself. Elements heavier than iron, including gold, platinum, and uranium, are created only in these violent stellar deaths. The shock wave also triggers star formation in nearby gas clouds, seeding the galaxy with the next generation of stars. What remains after the explosion depends on the star's original mass. Stars between 8 and 25 times the mass of our sun leave behind neutron stars, objects so dense that a teaspoon of neutron star material would weigh as much as Mount Everest. More massive stars collapse into black holes, regions of space-time where gravity is so strong that not even light can escape. But the true power behind these stellar explosions, and indeed the entire galaxy, comes from something we cannot see, something that shapes the cosmos from the shadows. Surrounding every star, every gas cloud, every bright spiral arm in the Triangulum Galaxy is a vast scaffolding built from matter we cannot see or touch. Dark matter makes up 85% of all matter in the universe, yet it interacts with ordinary matter only through gravity. It doesn't emit light, doesn't absorb light, and doesn't reflect light. It's like trying to map an invisible city by watching how people move through its streets, inferring the locations of buildings from the patterns of foot traffic. The first clues to dark matter's existence came from studying galaxy rotation curves. When astronomers measured how fast stars orbit the galactic center, they discovered something impossible. According to the visible matter in the galaxy, stars in the outer regions should move much slower than those near the center, just like planets in our solar system. But the observations showed something different. Stars throughout the galaxy move at nearly the same speed, regardless of their distance from the center. It's like watching a merry-go-round where all the horses gallop at the same pace, whether they're on the inner ring or the outer edge. The only way to explain this is if the galaxy contains 5 times more mass than we can see. This invisible mass forms a roughly spherical halo around the galaxy, extending far beyond the visible stars. Computer simulations show that without this dark matter halo, the Triangulum Galaxy would have torn itself apart billions of years ago. The spiral arms would have unwound, the gas would have been flung into intergalactic space, and star formation would have ceased. The dark matter halo acts like a cosmic gravitational net, holding the galaxy together while remaining completely invisible. It's the ultimate cosmic construction project, a scaffold built from exotic particles that don't interact with ordinary matter except through their gravitational influence. But what exactly is dark matter? The honest answer is that we don't know. It could be composed of weakly interacting massive particles, hypothetical entities that were predicted by particle physics theories but have never been detected. It could be axions, incredibly light particles that barely interact with anything. Or it could be something completely unexpected, a form of matter so alien that our current physics cannot even describe it. The mystery deepens when we realize that dark matter was crucial to the formation of the universe itself. In the early cosmos, tiny fluctuations in the dark matter density grew under their own gravity, creating the first structures in the universe. These dark matter halos became the seeds around which galaxies formed, providing the gravitational wells that allowed ordinary matter to collapse and ignite the first stars. Without dark matter, the universe would be a very different place. Galaxies would be smaller and less stable. Star formation would be less efficient. The cosmic web of filaments and voids that connects galaxies across billions of light-years would never have formed. We might be living in a universe with no large-scale structure at all, just isolated stars drifting through empty space. The search for dark matter has become one of the greatest detective stories in science. Deep underground laboratories shield sensitive detectors from cosmic rays, waiting for the telltale signature of a dark matter particle collision. Particle accelerators smash protons together at nearly the speed of light, hoping to create dark matter particles in high-energy collisions. Space telescopes scan the cosmos for the gravitational signatures of dark matter clumps. Yet, despite decades of searching, dark matter remains as elusive as ever. It's everywhere and nowhere, holding the universe together while remaining completely invisible to our instruments. The Triangulum Galaxy is embedded in an ocean of dark matter, swimming through an invisible medium that shapes its destiny. But within this dark ocean, brilliant beacons of light announce the birth of new stars with spectacular displays of cosmic fireworks. Deep within the Triangulum Galaxy's spiral arms, cosmic nurseries blaze with the light of millions of newborn suns. The largest of these star-forming regions, NGC 604, shines with the combined brightness of 600,000 stars, like our Sun. This single stellar nursery contains enough energy to power our entire solar system for billions of years. From a distance, it appears as a rosy glow against the dark backdrop of space, but up close, it reveals itself as a churning cauldron of creation and destruction. The region spans more than 1,000 light-years, making it larger than the distance between our Sun and the nearest star. Within this vast expanse, gravity is sculpting the raw materials of space into the next generation of stars. Towering pillars of gas and dust, some reaching heights of several light-years, serve as stellar incubators where new suns are taking their first breaths. These pillars are both beautiful and temporary. They're carved by the intense radiation and stellar winds from nearby massive stars, which act like cosmic sandblasters, eroding the gas columns while simultaneously triggering new star formation within them. The process is a delicate balance between creation and destruction, with each new star contributing to the forces that will eventually disperse the very cloud that gave it birth. The youngest stars in these regions are still embedded in their birth cocoons, visible only in infrared light that can penetrate the surrounding dust. These stellar embryos are fed by accretion disks of swirling material that spiral inward, growing hotter and brighter as they approach the star's surface. Some of these disks may be forming planetary systems, laying the groundwork for future worlds. The most massive stars in these regions burn so brightly they ionize the surrounding gas, creating glowing bubbles of plasma that expand like cosmic soap bubbles. These emission nebulae paint the star-forming regions in vibrant colors, with red hydrogen, blue oxygen, and green doubly ionized oxygen, creating a palette that would make any artist envious. The energy output from these stellar nurseries is staggering. A single massive star can produce as much energy in 1 second as our Sun produces in an entire year. When dozens or hundreds of these giants form in the same region, they create stellar associations that can outshine entire galaxies. The radiation pressure from these young stars is so intense it can blow away the remaining gas in the region, effectively shutting down further star formation. But the influence of these stellar nurseries extends far beyond their visible boundaries. The hot gas they produce rises above the galactic disk, creating fountains of enriched material that rain back down onto the galaxy. This galactic fountain carries heavy elements forged in stellar cores to regions where they can be incorporated into the next generation of stars and planets. The stellar winds from massive stars collide and interact, creating superbubbles of hot gas that can grow to hundreds of light-years in diameter. These bubbles serve as cosmic mixing bowls, stirring the interstellar medium and distributing heavy elements throughout the galaxy. When the most massive stars explode as supernovas, they add even more energy to these bubbles, sometimes breaking through the galactic disk entirely. The life cycle of a star-forming region follows a predictable pattern. It begins with the gravitational collapse of a giant molecular cloud, triggered by some external disturbance. Star formation proceeds rapidly, with the most massive stars forming first. These giants quickly begin to disrupt their birth environment, carving out cavities in the gas and eventually dispersing the cloud entirely. The entire process takes only 10 to 20 million years, a brief moment in galactic time. But during this cosmic instant, these stellar nurseries transform the galaxy, enriching it with heavy elements and organizing the interstellar medium into the complex structures we observe today. Yet even as these bright beacons of star formation illuminate the galaxy, ancient stellar cities hold secrets from the galaxy's distant past. Orbiting the Triangulum Galaxy like ancient sentinels are stellar time capsules that preserve the memory of the universe's youth. Globular clusters are among the oldest objects in the galaxy, spherical collections of hundreds of thousands to millions of stars bound together by their mutual gravity. These stellar cities formed when the universe was less than 1 billion years old, making them living fossils from the cosmic dawn. Each cluster tells a story that spans nearly the entire history of the cosmos. The stars within these clusters are all roughly the same age, born from the same primordial gas cloud in a single burst of star formation. Unlike the star-forming regions we see today, these ancient stellar nurseries were composed almost entirely of hydrogen and helium, the simplest elements forged in the Big Bang. Heavy elements like carbon, oxygen, and iron were virtually absent, creating a generation of stars unlike any being born today. This chemical purity makes globular cluster stars living laboratories for understanding stellar evolution. Without heavy elements to complicate their nuclear fusion processes, these stars follow predictable evolutionary paths. The most massive stars have long since exploded as supernovas or evolved into white dwarfs, leaving behind populations of smaller, longer-lived stars that will shine for trillions of years. The Triangulum Galaxy hosts several dozen globular clusters, each containing clues about the galaxy's formation and early history. These clusters didn't form where we see them today. When they were born, the galaxy was a chaotic, turbulent place, with gas clouds colliding and merging in a cosmic dance of destruction and creation. The clusters formed in the dense cores of these colliding clouds, then survived the galaxy's violent youth to become the ancient relics we observe today. The distribution of globular clusters around the galaxy reveals the shape of the dark matter halo that surrounds it. Unlike the stars in the galactic disk, which follow circular orbits, globular clusters trace elongated elliptical paths that carry them far above and below the galactic plane. These orbits map out the three-dimensional structure of the galaxy's invisible dark matter scaffolding. Each cluster is a gravitational masterpiece, with stars packed so densely that the night sky from a planet within the cluster would be ablaze with thousands of bright stars. The gravitational interactions between these stars create a complex dance where stellar encounters can fling stars out of the cluster or cause them to spiral inward toward the center. Over billions of years, this gravitational evolution has sculpted the clusters into the perfect spherical shapes we observe today. The cores of globular clusters harbor some of the most exotic objects in the universe. Neutron stars, the ultra-dense remnants of supernova explosions, can be found spinning rapidly as pulsars, lighthouse beacons that sweep the galaxy with beams of radiation. Some clusters may even contain intermediate mass black holes, objects too massive to form from single stellar collapse but too small to be the supermassive black holes found at galactic centers. But perhaps the most remarkable aspect of globular clusters is their role as cosmic chronometers. By studying the colors and brightness of stars within these clusters, astronomers can determine their ages with precision. The oldest clusters in the Triangulum Galaxy are nearly 13 billion years old, formed when the universe was less than 1 billion years old. They're among the first generation of stellar systems to form after the Big Bang. These ancient stellar cities have witnessed the entire history of galaxy formation. They've seen the galaxy grow from a small, chaotic collection of gas clouds into the majestic spiral we observe today. They've survived countless close encounters with other clusters, the disruption of galactic mergers, and the gradual chemical enrichment of the galaxy through successive generations of star formation. As we peer into these globular clusters, we're looking back in time to an era when the universe was young and the first stellar civilizations were taking shape. But the galaxy's structure is more dynamic than these ancient clusters might suggest, with spiral arms acting as cosmic highways that channel the flow of gas and stars. The elegant spiral arms of the Triangulum Galaxy aren't just beautiful decorations, they're cosmic highways that channel the flow of matter and energy across tens of thousands of light years. From our perspective, the galaxy's spiral structure appears static and permanent, like a frozen whirlpool in space. But this is an illusion created by the vast timescales involved. The spiral arms are actually waves of compression traveling through the galactic disk, similar to traffic jams that move along a highway even though individual cars enter and exit the jam. This phenomenon, called spiral density wave theory, explains one of the galaxy's most puzzling features. If the spiral arms were simply material structures rotating with the galaxy, they would have wound up completely after just a few rotations, destroying the spiral pattern. Instead, the arms persist because they're pressure waves, regions where the density of stars and gas is temporarily higher than average. As material orbits the galaxy, it encounters these density waves like a car approaching a traffic jam. The gas clouds slow down, compress, and pile up in the spiral arms. This compression triggers star formation, lighting up the arms with bright young stars and glowing nebulae. The most massive stars burn out quickly, fading before they can move far from their birth sites, which is why the spiral arms appear so prominently in blue light. The process creates a cosmic conveyor belt of star formation. Gas flows into the spiral arms from the spaces between them, gets compressed into dense clouds, forms stars, and then disperses as stellar winds and supernova explosions blow the remaining gas back into the interarm regions. This cycle repeats every few 100 million years as the galaxy rotates. The spiral arms also act as cosmic rivers, channeling gas from the outer galaxy toward the center. This radial flow of material helps explain how galaxies can maintain star formation over billions of years. Without this inward transport of gas, the central regions would quickly exhaust their fuel for making new stars. But the spiral structure isn't perfectly stable. Computer simulations show that spiral arms can strengthen, weaken, split, and merge over time. The Triangulum Galaxy's current two-armed spiral pattern may be temporary, possibly the result of a recent gravitational interaction with a neighboring galaxy or the passage of a massive gas cloud. The arms also create different environments within the galaxy. The spaces between the spiral arms are relatively quiet, with lower rates of star formation and fewer supernova explosions. These interarm regions may be more hospitable to the development of complex life, shielded from the intense radiation and stellar violence that characterizes the spiral arms themselves. The magnetic field of the galaxy follows the spiral structure, creating invisible highways for charged particles. Cosmic rays, high-energy particles accelerated by supernova explosions, follow these magnetic field lines as they propagate through the galaxy. This creates a complex three-dimensional structure where the visible spiral arms are just one component of a much larger architectural framework. The spiral arms also influence the chemical evolution of the galaxy. Star formation in the arms produces heavy elements that are dispersed by stellar winds and supernova explosions. These elements mix with the interstellar medium and eventually make their way to the interarm regions, where they can be incorporated into the next generation of stars. This creates a gradient of heavy element abundance that varies both with distance from the galactic center and with position relative to the spiral arms. Recent observations have revealed that the spiral arms may be more dynamic than previously thought. Some regions show evidence of spur-like structures branching off from the main arms, creating a more complex pattern than the simple two-armed spiral. These features may be temporary, created by local instabilities in the galactic disk, or by the gravitational influence of massive star-forming regions. The study of spiral structure in the Triangulum Galaxy has implications far beyond our local galactic neighborhood. Understanding how spiral arms form and evolve helps us interpret observations of distant galaxies and provides insights into the fundamental physics of galactic dynamics. But at the heart of this grand spiral design lies the galaxy's most mysterious region, where the normal rules of stellar behavior may not apply. At the center of the Triangulum Galaxy lies a region so dense with stars and shrouded in dust that we're only beginning to understand its true nature. The galactic core, or nucleus, represents less than 1% of the galaxy's total volume, but contains a disproportionate share of its most exotic phenomena. Here, stars are packed together at densities thousands of times higher than in our solar neighborhood. The night sky from a planet in this region would be ablaze with brilliant stars, many bright enough to cast shadows. Unlike the supermassive black holes that lurk at the centers of larger galaxies, the Triangulum Galaxy's core appears to lack such a monster. This makes it unusual among spiral galaxies, most of which harbor central black holes containing millions or billions of times the mass of our Sun. The absence of a supermassive black hole suggests that the Triangulum Galaxy may have had a different evolutionary history than its larger cousins. Instead of a central black hole, the core region contains a dense concentration of older stars, many of them red giants and supergiants that have evolved beyond their main sequence lifetimes. These stellar elders dominate the infrared light from the galactic center, creating a warm glow that can be detected even through the obscuring dust clouds that surround the region. The dust itself tells a story of stellar death and renewal. Much of it consists of heavy elements forged in the cores of dying stars and dispersed through supernova explosions and stellar winds. Silicon, carbon, and iron atoms that were created in stellar furnaces now drift as microscopic grains through the interstellar medium, absorbing and scattering starlight. This dust creates a cosmic fog that makes the galactic center one of the most challenging regions to study. Visible light from the core stars is almost completely absorbed, forcing astronomers to rely on infrared and radio observations that can penetrate the dusty veil. Each new wavelength reveals different aspects of the core's structure and activity. Recent infrared surveys have revealed an unexpected level of star formation activity in the central region. Despite the apparent lack of a supermassive black hole, the core shows signs of recent stellar births, with young hot stars scattered throughout the older stellar population. This suggests that gas is still flowing into the center and collapsing to form new stars, possibly triggered by spiral arm dynamics or past gravitational interactions. The core also contains several unusual stellar objects that may be the products of the extreme environment. Close stellar encounters in the dense core can strip matter from one star and transfer it to another, creating exotic binary systems and stellar remnants. Some of these objects may be blue stragglers, stars that appear younger than their surroundings because they've been rejuvenated by mass transfer or stellar mergers. X-ray observations have revealed another layer of complexity in the galactic center. Hot gas with temperatures exceeding millions of degrees creates a diffuse glow that extends throughout the core region. This gas may be heated by shock waves from supernova explosions or by the collective stellar winds from the massive stars in the region. The magnetic field in the galactic core is particularly strong and complex, twisted into intricate patterns by the rotation of the galaxy and the turbulent motions of the gas. These magnetic fields may play a crucial role in channeling gas flows and influencing star formation rates in the central region. Perhaps most intriguingly, the core shows evidence of past violent activity. Expanding shells of hot gas suggest that the region has experienced periods of enhanced star formation and supernova activity in the past. These starbursts may have been triggered by gravitational interactions with other galaxies or by the infall of large gas clouds from the outer regions. The study of the Triangulum Galaxy's core provides a unique laboratory for understanding galactic evolution. Unlike the violent, active cores of larger galaxies dominated by supermassive black holes, this quieter nucleus allows us to study the more subtle processes that shape galactic centers over cosmic time. As we continue to peer through the cosmic dust with ever more sophisticated instruments, the secrets of the galactic heart slowly reveal themselves, each discovery adding another piece to the puzzle of how galaxies form, evolve, and eventually meet their fate in the cosmic dance of the universe. In the heart of the Triangulum Galaxy's most active regions, stellar metropolises burn with the collective light of millions of suns. These massive star clusters, some containing over 1 million individual stars, shine so brightly they can be seen from billions of light years away. The largest of these stellar cities, known as superclusters, pack more luminous mass into a few dozen light years than our entire local galactic neighborhood contains in 1,000 light years. The most spectacular of these clusters formed in violent bursts of star formation triggered by galactic collisions or the passage of massive gas clouds. When conditions are just right, a single molecular cloud can collapse to form not just a few scattered stars, but an entire stellar civilization all at once. The gravitational collapse happens so rapidly that millions of stars ignite within a few million years, creating a stellar fireworks display that outshines entire dwarf galaxies. These newborn stellar cities are dominated by the most massive stars in the universe, blue and white supergiants that burn with temperatures exceeding 50,000 degrees. The combined radiation from these stellar titans creates a pressure so intense it can blow away entire star-forming regions, carving out vast cavities in the interstellar medium. The energy output from a single massive cluster can exceed the luminosity of 100 million stars like our Sun. The clusters themselves are gravitational masterpieces, with stars orbiting their common center of mass in complex patterns that have been refined over millions of years. The most massive stars sink toward the center through gravitational interactions, while smaller stars are flung toward the outer regions. This process, called mass segregation, creates a stellar hierarchy where the biggest and brightest stars dominate the cluster core. But these stellar cities are not permanent fixtures. The same massive stars that make them so luminous also seal their fate. Within just a few million years, the most massive stars begin to explode as supernovas, adding their energy to the stellar winds that are already pushing against the cluster's boundaries. Each supernova explosion sends shockwaves rippling through the cluster, potentially triggering new star formation while simultaneously dispersing the gas that could fuel future stellar births. The most violent clusters experience what astronomers call a supernova chain reaction. One massive star explodes, compressing nearby gas clouds and triggering the formation of even more massive stars. These new giants burn through their fuel rapidly and explode in turn, creating a cascade of stellar death that can illuminate the entire cluster for thousands of years. Some of these stellar cities are so massive they approach the boundary between star clusters and dwarf galaxies. The largest contain enough material to form their own gravitational wells, trapping gas and dust that can fuel multiple generations of star formation. These objects blur the line between stellar associations and true galaxies, representing a transitional class of cosmic structures. The stellar winds from massive clusters create superbubbles of hot gas that can grow to thousands of light years in diameter. These bubbles serve as cosmic laboratories where the interstellar medium is heated, compressed, and enriched with heavy elements. The expanding shells of gas eventually break through the galactic disk, creating fountains of hot material that rain back down onto the galaxy. The light from these stellar cities can be seen across vast distances, serving as beacons that mark the locations of the most active star-forming regions in the universe. When we observe distant galaxies, the bright knots of light we see are often massive star clusters similar to those in the Triangulum Galaxy, cosmic lighthouses that guide our understanding of galactic evolution. Yet even these brilliant stellar cities cannot match the destructive power of the expanding caverns carved by ancient stellar explosions. Scattered throughout the Triangulum Galaxy are vast hollows in space, cosmic caverns carved by the violent deaths of massive stars. These supernova remnants are the expanding shells of debris left behind when stars explode with the force of 10 billion hydrogen bombs detonating every second for millions of years. The blast waves from these explosions race through space at speeds exceeding 10,000 kilometers per second, sweeping up interstellar gas and dust like cosmic snowplows. The process begins with a catastrophic collapse. When a massive star exhausts its nuclear fuel, its core implodes in less than a second, rebounding in an explosion that can outshine an entire galaxy. The shock wave from this explosion rips through the star's outer layers, heating them to temperatures exceeding 1 billion degrees and flinging them into space at a significant fraction of the speed of light. This expanding shell of stellar debris crashes into the surrounding interstellar medium like a cosmic tsunami. The collision creates a double shock wave system, with one shock moving outward into the interstellar gas and another moving inward through the ejected stellar material. The region between these shocks becomes a furnace, where gas is heated to millions of degrees, creating a glowing bubble of plasma that can be detected across the electromagnetic spectrum. The supernova remnant grows larger and fainter as it expands, eventually reaching diameters of hundreds of light years. During this evolution, the remnant acts as a cosmic particle accelerator, using magnetic fields and shock waves to accelerate particles to nearly the speed of light. These cosmic rays then propagate throughout the galaxy, carrying energy and information about stellar explosions across vast distances. The shapes of supernova remnants tell stories of stellar violence and interstellar architecture. Some form perfect spheres, expanding uniformly in all directions through a homogeneous medium. Others create complex filamentary structures that trace the magnetic field lines and density variations in the surrounding space. The most spectacular remnants form intricate lacework patterns of glowing gas, with delicate filaments and knots that reveal the turbulent physics of shockwave propagation. These cosmic caverns have profound effects on their galactic neighborhoods. The hot gas they create rises above the galactic disk, forming chimneys and fountains that transport heavy elements from the disk to the galactic halo. This process helps regulate the chemical evolution of the galaxy, ensuring that elements forged in stellar cores are distributed throughout the galactic ecosystem. The energy injection from supernova remnants also influences star formation rates in nearby regions. The shock waves can trigger the collapse of molecular clouds, initiating new episodes of stellar birth. But the same explosions can also disrupt star-forming regions, heating the gas to temperatures too high for gravitational collapse. This creates a complex feedback loop where stellar death influences stellar birth across multiple generations. Some supernova remnants interact with each other, creating superbubbles when multiple explosions occur in the same region. These enormous cavities can grow to thousands of light years in diameter, dominating the structure of the interstellar medium over vast regions. The largest superbubbles can break through the galactic disk entirely, creating pathways for gas to flow between the disk and the halo. The study of supernova remnants provides crucial insights into stellar evolution, interstellar physics, and galactic dynamics. Each remnant is a natural laboratory where extreme conditions create phenomena that cannot be reproduced on Earth. But even these violent stellar explosions pale in comparison to the cosmic ballet performed by binary star systems dancing toward their doom. Throughout the Triangulum Galaxy, millions of binary star systems perform an elegant gravitational ballet that will end in violence. More than half of all stars in the galaxy are born in pairs or groups, locked in orbital embraces that can last billions of years. These cosmic couples dance around their common center of mass, their gravitational attraction maintaining a delicate balance between approaching too close and drifting apart. But this celestial waltz is not eternal. Time, stellar evolution, and the inexorable pull of gravity conspire to create endings more dramatic than any terrestrial tragedy. The most common fate awaits systems where one star is significantly more massive than its companion. The massive star evolves faster, exhausting its nuclear fuel first and swelling into a red giant. As it expands, its outer layers reach the point where the companion star's gravity becomes stronger than its own. Material begins to flow from the giant to its smaller partner, creating a bridge of glowing gas between the two stars. This mass transfer fundamentally changes both stars. The donor star loses mass and can actually extend its lifetime by shedding its outer layers. The recipient star, meanwhile, gains mass and brightens dramatically. In some cases, the infalling material forms an accretion disk around the smaller star, heating up to millions of degrees and creating a brilliant source of X-rays. The mass transfer process is rarely smooth or steady. The flow of material can be unstable, creating nova explosions when enough hydrogen accumulates on the surface of the receiving star. These novae can temporarily make the system 10,000 times brighter than normal, creating stellar fireworks that can be seen from great distances across the galaxy. But some binary systems are destined for even more spectacular endings. When both stars are massive enough to form neutron stars or black holes, the system enters a death spiral that can last millions of years. The two compact objects orbit each other with increasing speed, their orbital energy carried away by gravitational waves that ripple through the fabric of space-time itself. As the orbit shrinks, the two objects spiral inward, like water circling a drain. The final moments of this cosmic dance occur in a matter of seconds, with the neutron stars or black holes orbiting each other hundreds of times per second before finally colliding. The merger releases more energy and gravitational waves than all the visible stars in the observable universe combined. These kilonova explosions create conditions so extreme they forge heavy elements that cannot be produced in normal stellar cores. Gold, platinum, and uranium are created in the intense heat and pressure of the merger, then scattered into the interstellar medium, where they can be incorporated into future generations of stars and planets. The gold in our jewelry, the platinum in our electronics, all may have been forged in the violent merger of neutron stars billions of years ago. The Triangulum Galaxy hosts thousands of these binary systems at various stages of their evolution. Some are just beginning their dance, young pairs of stars that will orbit each other for billions of years. Others are approaching their final acts, with white dwarf stars slowly consuming their companions, or neutron stars spiraling toward merger. The study of binary star evolution has revealed that stellar death is far more complex and violent than once thought. Single stars may end their lives quietly, fading into white dwarf obscurity. But binary systems can experience multiple episodes of mass transfer, nova explosions, and ultimately catastrophic mergers that reshape the galaxy around them. These cosmic partnerships also serve as natural laboratories for testing our understanding of stellar physics and gravitational dynamics. The precise timing of pulsar binary systems has allowed astronomers to detect gravitational waves indirectly, confirming one of Einstein's boldest predictions decades before direct detection became possible. Yet even these violent stellar deaths contribute to a grander cosmic artistry, creating some of the most beautiful structures in the universe. Across the Triangulum Galaxy, dying stars create masterpieces that rival the greatest works of art ever conceived by human imagination. These planetary nebulae are cosmic paint palettes where physics becomes artistry. Each nebula displays a unique combination of colors created by different elements glowing at specific temperatures and densities. The red glow comes from hydrogen, the universe's most abundant element, while oxygen produces ethereal blues and greens. Nitrogen adds touches of deep red, and sulfur contributes yellows and oranges to the cosmic canvas. But the true artistry lies in the nebula's structure, shaped by forces as complex as any master painter's technique. The dying star at the center doesn't simply puff off its outer layers uniformly. Instead, magnetic fields, stellar rotation, and the presence of companion stars sculpt the expanding gas into intricate patterns that defy easy explanation. Some nebulae form perfect rings, like cosmic smoke rings expanding through space. Others create hourglass shapes, with narrow waists and bulbous ends that suggest the influence of equatorial disks around the central star. The most complex nebulae resemble butterflies, flowers, or even human eyes, with symmetrical patterns that seem almost intentionally designed. The Helix Nebula, sometimes called the Eye of God, demonstrates the incredible precision of these cosmic sculptures. Its intricate braided structure contains thousands of individual knots and filaments, each one a story of gas compression and magnetic field interaction. The nebula's colors shift from deep red at the edges to brilliant blue-green in the center, creating a three-dimensional artwork that spans several light years. The creation of these colors involves quantum physics at its most fundamental level. When the central white dwarf star bombards the surrounding gas with ultraviolet radiation, it strips electrons from atoms, ionizing the gas and causing it to glow. Each element glows at specific wavelengths determined by the energy levels of its electrons. The result is a spectrum of colors that serves as a fingerprint for the elements present in the nebula. The intensity and distribution of these colors reveal the history of the dying star. Red regions indicate areas where the ultraviolet radiation is weaker, allowing hydrogen to remain partially neutral. Blue-green regions mark zones of intense ionization, where oxygen atoms have been stripped of multiple electrons. The boundaries between different colored regions trace the shock fronts and density variations within the expanding gas. Some nebulae change their appearance over human timescales, allowing astronomers to watch the cosmic artwork evolve in real time. The expansion of the gas shells creates moving patterns of light and shadow as different regions brighten and fade. Knots of denser gas can be seen streaming away from the central star like cosmic fireworks, while cavities carved by stellar winds create hollow spheres within the larger nebula. The symmetry of many planetary nebulae suggests that binary star systems play a crucial role in their formation. A companion star orbiting the dying giant can create jets of gas that punch through the stellar envelope, creating the bipolar structures seen in many nebulae. The gravitational influence of the companion can also create spirals and rings, as the gas is shaped by orbital dynamics. These cosmic artworks are temporary, lasting only tens of thousands of years before the expanding gas becomes too diffuse to glow brightly. But in that brief moment of cosmic time, they transform the ordinary death of a star into something transcendent, creating beauty from destruction and order from chaos. The study of planetary nebulae has revealed the incredible diversity of stellar death. No two nebulae are exactly alike, each one a unique expression of the physical processes that govern stellar evolution. They serve as laboratories for understanding atomic physics, fluid dynamics, and electromagnetic fields under conditions that cannot be replicated on Earth. But these gentle stellar deaths are not the only way that stars shed their outer layers into space. Some stars choose a more violent path, stripping themselves bare through stellar winds that rage with hurricane force. In the most violent star-forming regions of the Triangulum Galaxy, stellar monsters are literally blowing themselves apart. Wolf-Rayet stars are among the most extreme objects in the universe, massive suns that have been stripped down to their nuclear-burning cores by their own stellar winds. These stellar hurricanes rage at speeds exceeding 2,000 kilometers per second, carrying away the equivalent of Earth's entire mass every year. The winds are so powerful they can be detected from thousands of light years away, creating expanding bubbles of hot gas that dwarf entire solar systems. These stellar extremists begin their lives as the most massive stars in the galaxy, giants containing 50 to 100 times more mass than our Sun. But their enormous size becomes their weakness. The nuclear fusion in their cores burns so fiercely that the radiation pressure pushes against their outer layers with incredible force. Eventually, this pressure overcomes the star's gravitational grip, launching the outer atmosphere into space at hypersonic speeds. The stellar wind from a Wolf-Rayet star is not a gentle breeze, but a hurricane of atomic particles. The mass loss rate can exceed 1/1,000,000th of a solar mass per year, meaning these stars lose the equivalent of our entire Sun's mass in just a few million years. The expelled material carries away not just mass, but also angular momentum, causing the star to spin faster as it shrinks, like a figure skater pulling in their arms. What remains after this stellar stripping is a naked stellar core, burning helium and heavier elements in a nuclear furnace that reaches temperatures of 100 million degrees. The surface temperature of these exposed cores can exceed 50,000 degrees, making them some of the hottest stars known. They shine with a brilliant blue-white light that ionizes gas across vast distances, creating glowing nebulae that can be seen from outside the galaxy. The stellar winds from Wolf-Rayet stars don't expand uniformly. Instead, they create complex structures shaped by the star's magnetic field, rotation, and the presence of companion stars. Some winds form spiral patterns as they interact with binary companions, while others create bipolar outflows that shoot jets of material in opposite directions. The most spectacular Wolf-Rayet nebulae resemble cosmic roses or butterflies, with delicate petals of glowing gas arranged in beautiful symmetrical patterns. These stellar winds carry heavy elements forged in the star's core out into the interstellar medium. Carbon, oxygen, and nitrogen, produced by nuclear fusion, are dispersed across the galaxy, enriching the raw materials for future star formation. Some Wolf-Rayet stars produce so much carbon that they create sooty clouds of carbon dust, painting dark silhouettes against the bright background of star-forming regions. The interaction between Wolf-Rayet winds and the surrounding interstellar medium creates some of the most energetic phenomena in the galaxy. When these high-speed winds collide with nearby gas clouds, they create shock waves that can trigger new episodes of star formation. The winds can also carve out vast cavities in the interstellar medium, creating bubble-like structures that can grow to hundreds of light years in diameter. But the most dramatic aspect of Wolf-Rayet evolution is how it ends. Having stripped away their outer layers, these stars have exposed their cores to space, creating conditions that lead to some of the most violent explosions in the universe. The lack of a massive hydrogen envelope means that when these stars finally explode as supernovas, they produce different types of explosions than normal massive stars. Some Wolf-Rayet stars may produce hypernova explosions, events so energetic they can create gamma-ray bursts that outshine entire galaxies. These explosions are thought to be the birth sites of the most massive black holes and may be responsible for some of the heaviest elements in the universe. The study of Wolf-Rayet stars has revealed the incredible diversity of stellar evolution. These objects represent a brief but crucial phase in the lives of the most massive stars, a time when stellar winds reshape both the star and its surrounding environment. They serve as natural laboratories for studying extreme stellar physics and the complex interplay between nuclear fusion, stellar winds, and magnetic fields. Yet even these violent stellar winds cannot match the gradual dissolution that awaits the galaxy's more modest stellar communities. Scattered throughout the Triangulum Galaxy's spiral arms are stellar neighborhoods that are slowly dissolving, their members drifting apart like leaves scattered by an autumn wind. Open star clusters are the galaxy's most fragile communities, loose associations of hundreds to thousands of stars born from the same molecular cloud. Unlike the ancient, tightly bound globular clusters that orbit the galaxy's halo, these younger stellar groups are held together by weak gravitational bonds that weaken over time. They represent stellar families in the process of breaking apart, each member eventually destined to wander the galaxy alone. The dissolution process begins almost immediately after the cluster forms. The most massive stars, which sink toward the cluster's center through gravitational interactions, live fast and die young. When they explode as supernovas, they remove mass from the cluster and can even kick other stars out of the system entirely. Each stellar death weakens the cluster's gravitational grip on its remaining members. Meanwhile, the galaxy itself conspires against these stellar communities. As the cluster orbits the galactic center, it encounters tidal forces from the galaxy's gravitational field. These forces stretch the cluster, pulling stars away from its outer edges like ocean tides pulling sand from a beach. The process is gradual but relentless, stripping away the cluster's least bound members over millions of years. The cluster's journey through the galaxy also exposes it to gravitational perturbations from giant molecular clouds, spiral arms, and other stellar systems. Each encounter can scatter cluster members, sending them on new orbits that may never bring them back to their stellar family. It's like a cosmic game of billiards, where chance encounters determine which stars remain together and which are sent wandering into the galactic wilderness. Some clusters dissolve faster than others, depending on their initial mass, density, and location in the galaxy. Clusters born in the dense central regions of the galaxy face stronger tidal forces and more frequent encounters with other objects. Those formed in the outer regions may survive longer, but they too eventually succumb to the galaxy's disruptive influences. The Hyades cluster, one of the nearest open clusters to our solar system, exemplifies this dissolution process. The cluster's core still contains dozens of stars that share a common motion through space, but its outer regions have been stripped away over the past few 100 million years. Scattered throughout our local galactic neighborhood are individual stars that were once part of the Hyades, but have now drifted too far from their siblings to be easily recognized as cluster members. The dissolution of open clusters contributes to the galaxy's chemical evolution. Each cluster contains stars with similar ages and compositions, forged from the same primordial gas cloud. As these stars disperse throughout the galaxy, they carry with them the chemical signatures of their birth environments. The heavy elements they produce through nuclear fusion and stellar winds become mixed with the broader galactic medium, creating the complex chemical patterns we observe today. Some dissolved clusters leave behind streams of stars that share similar motions and compositions, creating moving groups that can be traced across the galaxy. These stellar streams are like fossil records of ancient cluster dissolution, allowing astronomers to reconstruct the history of stellar formation and dispersal over cosmic time. The study of cluster dissolution has revealed that the galaxy's stellar population is far more dynamic than once thought. Stars don't simply orbit the galactic center in isolation, but are part of complex flows and streams that reflect the galaxy's violent history. The Sun itself may have been born in an open cluster that dissolved billions of years ago, scattering its stellar siblings across the galaxy. The process of cluster dissolution also affects the potential for life in the galaxy. Stars born in clusters experience different radiation environments and gravitational perturbations than those born in isolation. The dissolution process can send stars into new regions of the galaxy, potentially exposing any planetary systems to different conditions than they experienced during their formation. Yet beneath all these visible stellar phenomena lies an invisible ocean that connects every star, every cluster, and every galaxy in the universe. Flowing through the vast spaces between stars is an invisible ocean that connects every corner of the Triangulum Galaxy in a complex web of matter and energy. The interstellar medium is far from empty space. This cosmic ocean contains roughly 1 atom per cubic centimeter, a density so low it would be considered a perfect vacuum by terrestrial standards. Yet across the galaxy's 60,000 light-year diameter, this tenuous material adds up to billions of solar masses of gas and dust, equal to about 10% of all the matter in the galaxy. This invisible ocean exists in multiple phases, each with its own temperature, density, and dynamics. The coldest regions are giant molecular clouds, where temperatures barely exceed absolute zero and hydrogen atoms combine to form molecules. These clouds are the galaxy's stellar nurseries, dense enough to collapse under their own gravity and give birth to new stars. Between these cold clouds flows a warm medium of neutral hydrogen, heated by starlight and cosmic rays to temperatures of several thousand degrees. This material fills much of the galaxy's volume, creating a tenuous atmosphere that permeates the space between star systems. It's like the air in a vast cosmic cathedral, invisible but essential to the structure of the whole. The hottest phase of the interstellar medium reaches temperatures exceeding 1 million degrees, created by supernova explosions and stellar winds from massive stars. This superheated plasma forms bubbles and cavities that can grow to hundreds of light years in diameter, creating a frothy structure that resembles cosmic sea foam. The hot gas rises above the galactic disk, creating fountains and chimneys that connect the disk to the galaxy's extended halo. These different phases don't exist in isolation, but are constantly interacting, trading mass and energy in a complex dance of thermodynamics. Cold clouds can be heated by shock waves from supernovas, while hot gas can cool and condense to form new molecular clouds. The result is a dynamic ecosystem where the conditions for star formation are constantly changing. The interstellar medium also serves as the galaxy's circulatory system, transporting heavy elements forged in stellar cores throughout the galactic ecosystem. When massive stars explode as supernovas, they inject carbon, oxygen, silicon, and iron into the surrounding medium. These elements mix with the existing gas, gradually enriching the galaxy's chemical composition and providing the raw materials for rocky planets and life itself. Magnetic fields thread through this cosmic ocean, creating invisible highways for charged particles and influencing the flow of gas on galactic scales. These magnetic fields can accelerate particles to nearly the speed of light, creating the cosmic rays that permeate the galaxy. They can also channel the flow of gas, creating filamentary structures that connect distant regions of the galaxy. The interstellar medium is also pervaded by radiation from stars, cosmic rays, and the cosmic microwave background. This radiation field provides the energy that ionizes atoms, dissociates molecules, and drives the chemical reactions that create complex molecules in space. In the densest regions, this radiation can be absorbed and re-emitted by dust grains, creating a complex interplay between matter and energy. Dust grains, though they represent only about 1% of the interstellar medium by mass, play a crucial role in its evolution. These microscopic particles, smaller than the wavelength of visible light, absorb starlight and re-emit it in the infrared. They also serve as catalysts for chemical reactions, providing surfaces where hydrogen atoms can combine to form molecules. The motion of the interstellar medium follows the galaxy's rotation, but it's far from uniform. Gas flows from the outer regions toward the center, driven by spiral arm dynamics and gravitational torques. This inward flow provides the fuel for continued star formation in the galaxy's central regions, while also mixing material from different parts of the galaxy. The study of the interstellar medium has revealed that galaxies are not simply collections of stars, but complex ecosystems where stars, gas, and dust interact in intricate ways. The medium serves as both the raw material for star formation and the repository for stellar death, creating a cycle of renewal that has continued for billions of years. But this invisible ocean is not calm. Racing through its depths are particles accelerated to incredible speeds by the galaxy's most violent phenomena. Invisible to our eyes, but carrying enormous energy, streams of subatomic particles race through the Triangulum Galaxy at speeds approaching the ultimate cosmic speed limit. Cosmic rays are not rays at all, but individual atomic nuclei, mostly protons and heavier atomic cores, that have been accelerated to nearly the speed of light by the galaxy's most violent phenomena. These subatomic bullets carry energies millions of times greater than anything produced in terrestrial particle accelerators, making them the most energetic particles in the known universe. The most powerful cosmic rays possess energies equivalent to a baseball thrown at 100 kilometers per hour, but concentrated into a single atomic nucleus smaller than a proton. When these ultra-high energy particles strike Earth's atmosphere, they create showers of secondary particles that can span kilometers and contain billions of individual particle interactions. The acceleration of cosmic rays to such extreme energies requires cosmic particle accelerators far more powerful than anything humans have built. Supernova shock waves are the prime suspects, using magnetic fields and plasma physics to accelerate particles through a process called diffusive shock acceleration. As particles cross back and forth across the shock front, they gain energy with each crossing, eventually reaching speeds where relativistic effects become important. The strongest accelerators in the galaxy are the remnants of supernova explosions, expanding shells of hot gas that can maintain their acceleration capabilities for thousands of years. These cosmic machines can accelerate particles to energies exceeding 100 billion electron volts, creating a population of high-energy particles that fills the galaxy like an invisible fog. But supernovas are not the only source of cosmic rays. The galaxy's most massive stars produce powerful stellar winds that can accelerate particles to high energies. The collision regions where these winds meet the interstellar medium create shock waves that serve as natural particle accelerators. Even the galaxy's central regions, though lacking a supermassive black hole, may contain acceleration sites where magnetic field interactions can boost particle energies. The highest energy cosmic rays, those with energies exceeding 100 billion electron volts, pose a particular mystery. These particles carry so much energy that they should interact with the cosmic microwave background radiation, losing energy through a process called the GZK cutoff. This means they can only travel about 50 million light-years before losing their energy, suggesting they must originate from sources within our local group of galaxies. Cosmic rays don't travel in straight lines through the galaxy. Instead, they follow complex trajectories determined by the galaxy's magnetic field, which acts like an invisible maze for charged particles. The magnetic field can trap cosmic rays, bouncing them back and forth across the galaxy for millions of years before they finally escape into intergalactic space. This magnetic trapping has important consequences for the galaxy's evolution. Cosmic rays carry pressure that can influence the dynamics of the interstellar medium, potentially affecting star formation rates and the structure of molecular clouds. They also contribute to the heating of the interstellar gas, helping to maintain the warm phase of the interstellar medium that fills much of the galaxy's volume. The study of cosmic rays has revealed that the galaxy is a much more dynamic and energetic place than visible light observations might suggest. These high-energy particles carry information about the galaxy's most violent events, serving as messengers from regions where normal matter is heated to billions of degrees, and magnetic fields reach strengths trillions of times stronger than Earth's magnetic field. When cosmic rays interact with the interstellar medium, they create secondary particles including gamma rays, neutrinos, and antimatter. These secondary particles can be detected by space-based observatories, providing a window into cosmic ray interactions throughout the galaxy. The distribution of gamma rays across the sky reveals the locations of cosmic ray acceleration sites and the structure of the galactic magnetic field. Some cosmic rays may even play a role in the evolution of life. The high-energy particles that constantly bombard planetary atmospheres can trigger chemical reactions that create complex organic molecules. They may also contribute to genetic mutations that drive biological evolution, though excessive cosmic ray exposure can also be harmful to life. The cosmic ray population in the Triangulum Galaxy represents a significant reservoir of energy, containing as much energy as all the starlight in the galaxy combined. This invisible component of the galactic ecosystem influences star formation, heats the interstellar medium, and may even affect the evolution of life on worlds throughout the galaxy. Yet even these high-energy particles follow invisible highways created by the galaxy's magnetic architecture. Threading through every cubic centimeter of the Triangulum Galaxy is an invisible scaffolding built from magnetic fields that shape the cosmos on the largest scales. The galaxy's magnetic field is roughly 1 million times weaker than Earth's magnetic field, so faint it would barely deflect a compass needle. Yet this tenuous field extends across tens of thousands of light years, creating a vast electromagnetic structure that influences everything from the birth of stars to the flow of cosmic rays. It's like a cosmic nervous system, an invisible network that connects distant regions of the galaxy through electromagnetic forces. This magnetic architecture follows the galaxy's spiral structure, with field lines that trace elegant curves through the galactic disk. The magnetic field is strongest in the spiral arms, where it's amplified by the compression of gas in these regions. It's weaker in the spaces between the arms, creating a complex three-dimensional pattern that mirrors the galaxy's visible structure. The magnetic field lines act like invisible highways for charged particles, channeling the flow of cosmic rays and hot plasma throughout the galaxy. Particles with electric charge become trapped along these field lines, spiraling around them in helical trajectories that can extend for thousands of light years. This creates a population of high-energy particles that fills the galaxy like an invisible atmosphere. The origin of galactic magnetic fields remains one of the great mysteries of astrophysics. Some theories suggest they were present from the galaxy's formation, remnants of primordial magnetic fields that existed in the early universe. Others propose that they were generated by dynamo processes, where the rotation of the galaxy amplifies weak seed fields over billions of years. The galactic dynamo operates like a cosmic generator, using the differential rotation of the galaxy to twist and amplify magnetic field lines. As the galaxy rotates, regions closer to the center move faster than those at the edge, stretching the magnetic field lines and increasing their strength. This process can amplify weak initial fields by factors of millions or billions over the galaxy's lifetime. The magnetic field also plays a crucial role in star formation, acting as both an enabler and an inhibitor of stellar birth. In molecular clouds, magnetic fields can support the gas against gravitational collapse, preventing stars from forming until the field is weakened or overcome by other forces. But magnetic fields can also channel the flow of gas, creating filamentary structures that serve as highways for material falling into star-forming regions. When stars do form, their births can disrupt the local magnetic field configuration. The powerful stellar winds from massive stars can drag magnetic field lines with them, creating complex magnetic structures around young stellar objects. These magnetic fields can help focus stellar winds into jets, creating the beautiful bipolar nebulae we observe around some young stars. The magnetic field also influences the galaxy's chemical evolution. Supernova explosions can create magnetic bubbles that trap heavy elements, preventing them from mixing with the broader interstellar medium. The magnetic field can also accelerate particles to high energies, creating cosmic rays that carry information about stellar explosions across vast distances. Recent observations have revealed that the magnetic field in the Triangulum Galaxy is not uniform, but contains complex structures including magnetic spirals, loops, and reversals. Some regions show evidence of magnetic field lines that have been twisted into helical configurations, possibly by the rotation of the galaxy or the influence of nearby galaxies. The interaction between the magnetic field and the interstellar medium creates a rich variety of plasma physics phenomena. Magnetic reconnection events can release enormous amounts of energy, heating gas to millions of degrees and accelerating particles to high energies. These processes may contribute to the heating of the interstellar medium and the acceleration of cosmic rays. The magnetic field also extends beyond the visible galaxy, creating a magnetosphere that may help protect the galaxy from intergalactic cosmic rays and other forms of high-energy radiation. This magnetic shield may be important for maintaining the galaxy's ability to form stars and support life over cosmic timescales. The study of galactic magnetic fields has revealed that galaxies are not simply gravitational systems, but complex magnetohydrodynamic structures where magnetic forces play crucial roles in their evolution. The invisible magnetic architecture of the Triangulum Galaxy represents a fundamental component of its structure, as important as the visible stars and gas in determining the galaxy's fate. But this elegant magnetic architecture exists within a larger puzzle that challenges our understanding of gravity itself. The Triangulum Galaxy is performing an impossible dance, one that violates the fundamental laws of physics as we understand them. When astronomers measure how fast stars orbit the galactic center, they discover something that should not exist. According to Newton's laws of gravitation, stars farther from the center should move more slowly than those closer in, just like planets in our solar system. Mercury races around the Sun at 47 kilometers per second, while distant Neptune crawls along at just 5 kilometers per second. This is the natural order of gravitational systems, but the Triangulum Galaxy laughs at these rules. Stars throughout the galaxy's disk move at roughly the same speed, about 100 kilometers per second, regardless of their distance from the galactic center. Some regions even show stars accelerating as they get farther out, as if the galaxy's gravitational pull somehow increases with distance. It's like watching a merry-go-round where the horses on the outer edge gallop faster than those near the center. This flat rotation curve, as astronomers call it, represents one of the most profound puzzles in modern astrophysics. If we add up all the visible matter in the galaxy, every star and gas cloud we can detect, we get only about 10% of the mass needed to produce the observed rotation speeds. The remaining 90% is missing, hidden in some form of matter that doesn't interact with light. The implications are staggering. If the rotation curve is correct, then everything we can see in the galaxy, every bright star and glowing nebula, represents just the tip of an enormous iceberg. The bulk of the galaxy's mass is invisible, detectable only through its gravitational effects on the visible matter. Three possibilities exist to explain this cosmic mystery. The first is that our understanding of gravity is fundamentally wrong, that Newton's and Einstein's theories break down on galactic scales. Some physicists have proposed modified theories of gravity that could explain the rotation curves without invoking invisible matter, but these theories struggle to explain other observations. The second possibility is that the galaxy contains vast amounts of ordinary matter that we simply cannot detect. This could include brown dwarfs, black holes, or dense molecular clouds too cold to emit detectable light. But detailed searches have failed to find enough of these objects to account for the missing mass. The third possibility is that the galaxy is embedded in a halo of exotic matter that interacts only through gravitational forces. This dark matter, as it's called, would outweigh all the visible matter in the galaxy by a factor of 5 to 1. Computer simulations show that such a dark matter halo could explain not only the rotation curve, but also the galaxy's stability over billions of years. The rotation curve also reveals the three-dimensional structure of the galaxy's mass distribution. The fact that the curve remains flat out to the galaxy's visible edge suggests that the dark matter halo extends far beyond the visible stars, possibly encompassing a volume hundreds of times larger than the luminous galaxy. We may be seeing only the bright core of a much larger, invisible structure. This dark matter halo would contain roughly 100 billion times the mass of our Sun, making it the dominant component of the galaxy's gravitational field. The visible stars and gas that create the galaxy's beautiful spiral structure would be mere passengers, carried along by the gravity of this invisible ocean of exotic matter. The study of rotation curves in thousands of galaxies has revealed that this phenomenon is universal. Every spiral galaxy shows the same pattern, with rotation speeds that remain roughly constant or even increase with distance from the center. This suggests that dark matter is not a peculiarity of our local cosmic neighborhood, but a fundamental component of the universe. The rotation curve of the Triangulum Galaxy continues to challenge our understanding of cosmology and particle physics. It suggests that the universe is far stranger and more complex than we imagined, dominated by forms of matter and energy that remain completely mysterious despite decades of intensive research. As we peer deeper into the galaxy's structure, we encounter phenomena that stretch the boundaries of known physics and hint at cosmic forces beyond our current understanding. The rotation curve is just the beginning of a journey into the unknown, where the familiar laws of nature may no longer apply. Hidden within the Triangulum Galaxy's stellar populations are ancient witnesses to cosmic catastrophes that shaped the galaxy's violent past. Each generation of stars carries the chemical fingerprints of its birth environment, creating a stellar archaeology that reveals the galaxy's tumultuous history. The oldest stars, formed when the universe was young and pristine, contain almost no heavy elements. They're composed of nearly pure hydrogen and helium, the only elements forged in the Big Bang's nuclear furnace. These ancient stellar fossils tell a story of galactic cannibalism and merger violence. When astronomers analyze their chemical compositions, they find evidence that the Triangulum Galaxy has devoured smaller companions throughout its history. Each merger event left its signature in the stellar populations, creating streams of stars with unusual chemical abundances and orbital patterns. The galaxy's stellar halo contains the most dramatic evidence of this violent past. Unlike the orderly rotation of disk stars, halo stars follow chaotic orbits that carry them far above and below the galactic plane. These stellar refugees are the survivors of galactic collisions, torn from their original homes and scattered into the galaxy's outer regions. Some halo stars move in retrograde orbits, traveling in the opposite direction to the galaxy's rotation. This backward motion is the smoking gun of galactic merger events, where the gravitational chaos of colliding galaxies can reverse stellar orbits and fling stars onto completely new trajectories. It's like finding cars driving backward on a highway, clear evidence of some past catastrophic event. The chemical abundances of stellar populations also reveal periods of enhanced star formation triggered by galactic interactions. When two galaxies collide, their gas reserves are compressed and stirred, triggering massive bursts of stellar birth. These starburst events create populations of stars with enhanced abundances of alpha elements like oxygen and magnesium, forged in the cores of massive stars that lived and died quickly during the chaotic merger. Different regions of the galaxy show distinct stellar populations, each telling part of the larger story. The galactic bulge contains older, more metal-poor stars that formed during the galaxy's earliest epochs. The disk populations show a gradient of chemical enrichment, with stars closer to the center generally containing more heavy elements than those in the outer regions. The spiral arms themselves create temporary stellar populations with characteristic ages and compositions. Stars born in the arms carry the chemical signatures of the compressed gas from which they formed, including enhanced abundances of elements produced by recent supernova explosions. As these stars age and drift away from their birth sites, they spread these chemical tracers throughout the galaxy. The most metal-rich stars in the galaxy are found in the youngest stellar populations, born from gas that has been enriched by billions of years of stellar evolution. These stars contain the full periodic table of elements, forged in successive generations of stellar cores and distributed by supernova explosions and stellar winds. By studying the ages, motions, and chemical compositions of millions of stars, astronomers can reconstruct the galaxy's merger history. Computer simulations suggest that the Triangulum Galaxy has experienced at least several major merger events, each one adding new stellar populations and disrupting the galaxy's structure. The ongoing collision with the Andromeda Galaxy, still billions of years in the future, will add another chapter to this stellar archaeological record. When future astronomers study the merged galaxy's stellar populations, they'll find evidence of our current epoch preserved in the chemical signatures and orbital patterns of the stars we see today. But these stellar storytellers are just one part of a larger cosmic cycle, where gravity continues to sculpt new worlds from the raw materials of space. Deep within the Triangulum Galaxy's spiral arms, colossal gas clouds are succumbing to the inexorable pull of their own gravity in a cosmic ballet of collapse and creation. Giant molecular clouds, containing enough material to build millions of stars, drift through space in a delicate balance between expansion and contraction. For millions of years, these clouds can remain stable, their internal pressure from random molecular motions perfectly balancing the inward pull of gravity. But this equilibrium is precarious, like a boulder balanced on a cliff edge, waiting for the slightest disturbance to trigger catastrophic change. The trigger often comes from outside the cloud itself. A shock wave from a nearby supernova explosion, the gravitational influence of a passing star, or the compression caused by spiral arm dynamics can tip the balance. Once gravity gains the upper hand, the collapse becomes inevitable, governed by the same physics that created our solar system 4.5 billion years ago. The collapse begins slowly, almost imperceptibly. The cloud contracts by just a few percent over thousands of years, gradually increasing its density while cooling toward absolute zero. But as the cloud becomes denser, its gravitational pull strengthens, accelerating the infall of material. What started as a gentle drift becomes a headlong plunge toward the center. As the gas compresses, it begins to fragment into smaller clumps, each destined to become a stellar nursery. The largest fragments may contain hundreds of times the mass of our Sun, while the smallest might have just enough material to form a single star. This fragmentation process is chaotic and unpredictable, governed by turbulence, magnetic fields, and the random motions of the gas itself. The collapsing fragments heat up as gravitational potential energy converts to thermal energy, following the same principle that makes a bicycle pump warm when you compress air. Temperatures that started near absolute zero climb to hundreds, then thousands of degrees. The gas begins to glow faintly in infrared light, marking the birth of what astronomers call protostars. But gravity's work is far from finished. As the protostar continues to contract, its core temperature climbs toward the 10 million degrees needed to ignite nuclear fusion. The journey from cold molecular cloud to burning star takes about 50 million years for a Sun-like star, but can happen much faster for more massive objects. The most massive protostars can ignite fusion in less than 1 million years, racing through their formation process like cosmic sprinters. The collapse isn't uniform or smooth. Magnetic fields threading through the gas can slow the infall, while rotation causes the material to flatten into a disk around the growing protostar. This disk becomes the birthplace of planetary systems, where dust grains stick together to form pebbles, then boulders, then planets. The same gravitational collapse that creates stars also sets the stage for the formation of worlds. Some collapsing clouds create not single stars but entire stellar systems. Multiple fragmentation can produce binary and triple star systems, where two or more stars orbit their common center of mass. In the densest regions, dozens or even hundreds of stars can form simultaneously, creating the open clusters that pepper the galaxy's spiral arms. The process of gravitational collapse operates on many scales throughout the galaxy. Individual stars form from the collapse of small gas clumps, but entire galaxies were created by the gravitational collapse of even larger structures in the early universe. The same fundamental physics governs the formation of planetary systems, star clusters, and the cosmic web of dark matter that scaffolds the universe. Computer simulations reveal that gravitational collapse is a hierarchical process, with smaller structures forming first and then assembling into larger ones. This bottom-up construction explains why we see such a rich variety of astronomical objects, from asteroids to galaxy clusters, all shaped by the same fundamental force. The collapse of gas clouds in the Triangulum Galaxy continues today, adding new stars to the cosmic census at a rate of about 1 solar mass per year. This ongoing star formation will eventually consume all the galaxy's gas reserves, bringing the era of stellar birth to a close billions of years in the future. But some collapses are not gentle affairs driven by gravity alone. When stellar violence intervenes, the results can trigger avalanches of creation across vast regions of space. Across the Triangulum Galaxy, the violent deaths of massive stars are triggering avalanches of stellar birth in a cosmic cycle where destruction enables creation. When a massive star explodes as a supernova, it doesn't simply disappear in a flash of light. The explosion creates a shock wave that races through space at speeds exceeding 10,000 kilometers per second, carrying the energy equivalent of our sun's entire lifetime output compressed into a few seconds. This expanding shell of superheated gas becomes a cosmic bulldozer, reshaping the galaxy's architecture and seeding the next generation of stars. The shock wave begins its journey when the star's core collapses and rebounds, sending a pressure pulse racing through the stellar envelope. Within hours, this wave breaks free from the dying star and plows into the surrounding interstellar medium. The collision creates temperatures exceeding 100 million degrees, hot enough to strip electrons from atoms and create a plasma so energetic it glows in X-rays. As the shock wave expands, it encounters the giant molecular clouds that drift through the galaxy's spiral arms. These clouds, which have existed in stable equilibrium for millions of years, suddenly find themselves under assault by a wall of superheated gas traveling faster than a speeding bullet. The gentle balance between gravity and pressure that kept them stable is shattered in an instant. The shock wave doesn't destroy these clouds, but compresses them, like a cosmic fist squeezing a sponge. The compression increases the cloud's density by factors of 10 or more, strengthening gravity's grip and triggering the gravitational collapse that leads to star formation. Regions that might have remained stable for millions more years suddenly begin their transformation into stellar nurseries. This process, called triggered star formation, can create spectacular bursts of stellar birth across vast regions of the galaxy. A single supernova can influence star formation over areas spanning hundreds of light years, potentially triggering the birth of thousands of new stars. These stellar babies will shine for millions or billions of years, carrying forward the legacy of the star that died to enable their creation. The shock waves don't just compress existing clouds, but also collect material from the diffuse interstellar medium, sweeping it up like cosmic snowplows. This collected material can form new molecular clouds in regions where none existed before, expanding the galaxy's star-forming capacity and spreading stellar birth into previously barren areas. The heavy elements dispersed by the supernova explosion also enrich the triggered star formation. The shock wave carries carbon, oxygen, silicon, and iron forged in the dying star's core, mixing these elements with the hydrogen and helium of the molecular clouds. The new stars that form will have higher abundances of heavy elements than their predecessors, enabling them to form rocky planets and potentially support the chemistry of life. Sequential star formation can create chains of stellar birth across the galaxy. When the first generation of triggered stars includes massive ones, they too will eventually explode as supernovas, creating new shock waves that can trigger even more star formation. This creates a propagating wave of stellar birth that can travel across entire spiral arms over tens of millions of years. The process is beautifully visible in the galaxy's star-forming regions, where we can see multiple generations of stars at different evolutionary stages. Young, hot blue stars mark the locations of recent shock-triggered star formation, while older red stars show where previous episodes occurred. The spatial arrangement of these stellar populations reveals the history of supernova-driven star formation across the region. Some of the galaxy's most spectacular stellar nurseries owe their existence to this process. The massive star-forming complexes that dominate the spiral arms often show evidence of triggered formation, with expanding bubbles of hot gas surrounding groups of young massive stars. These regions will eventually produce their own supernovas, continuing the cycle of death and birth that has operated throughout the galaxy's history. The efficiency of triggered star formation depends on the properties of the molecular clouds and the strength of the triggering shock wave. Dense, massive clouds are more easily triggered than diffuse ones, while stronger shocks can overcome the resistance of more stable clouds. This creates a complex interplay between stellar death and birth that influences the galaxy's overall star formation rate. But the galaxy's ability to form stars is not unlimited. Hidden beyond the visible stellar disk lies a vast reservoir of material that holds the key to the galaxy's ultimate fate. Beyond the furthest visible stars of the Triangulum Galaxy lies a vast empire of dark matter that extends 10 times farther than the light can reach, creating a cosmic structure larger than anything our eyes can perceive. The bright spiral arms and glowing star-forming regions that define our view of the galaxy represent only the luminous heart of a much larger gravitational system. Surrounding this visible disk is a roughly spherical halo of dark matter that contains 5 times more mass than all the visible stars combined. If we could see this invisible structure, the galaxy would appear as a vast, diffuse sphere rather than the elegant spiral we observe. This dark matter halo extends to distances of nearly 1 million light-years from the galactic center, making the true galaxy 15 times larger in diameter than its visible appearance suggests. The halo's outer boundary is so far from the galactic center that light from the galaxy's core takes 1 million years to reach its edge, longer than humans have existed as a species. The halo's gravitational influence shapes everything within it. The beautiful spiral structure we see exists only because the dark matter halo provides the gravitational scaffolding needed to maintain it. Without this invisible foundation, the galaxy's rotation would have wound up the spiral arms long ago, destroying the elegant pattern we observe today. Computer simulations reveal that the dark matter halo has a complex internal structure, with subhalos and density variations that reflect the galaxy's violent formation history. These substructures are the gravitational fossils of smaller dark matter clumps that merged to build the galaxy, each one adding its mass to the growing halo over billions of years. The halo also contains more than just dark matter. Scattered throughout this vast volume are ancient globular clusters, stellar streams from disrupted dwarf galaxies, and a diffuse population of halo stars that follow highly elliptical orbits. These objects serve as tracers of the halo's gravitational field, revealing its three-dimensional structure through their motions. Hot gas with temperatures exceeding 1 million degrees fills portions of the halo, creating a tenuous atmosphere around the galaxy. This gas is so hot and diffuse, it's invisible to optical telescopes but can be detected through its X-ray emission. The hot halo may contain as much mass as all the stars in the galaxy, representing a significant reservoir of baryonic matter hidden in the galaxy's outskirts. The boundary between the galaxy's halo and intergalactic space is not sharp but gradual, fading slowly into the cosmic web of dark matter that connects all galaxies. This transition region, called the galaxy's virial radius, marks the approximate limit of the galaxy's gravitational influence and defines the edge of its dark matter halo. Within this vast halo, smaller satellite galaxies orbit like planets around a star. These dwarf companions are embedded in their own dark matter subhalos, creating a hierarchical structure where halos exist within larger halos. The orbital motions of these satellites provide crucial information about the total mass and distribution of dark matter within the halo. The halo's rotation is much slower than that of the visible disk, creating a situation where the luminous galaxy spins within its dark matter envelope like a wheel within a wheel. This differential rotation may help explain some of the galaxy's observed properties, including the persistence of its spiral structure over cosmic time. Recent observations have detected streams of hydrogen gas extending far into the halo, possibly representing the remnants of gas accretion events that helped build the galaxy. These gas streams may be the visible traces of the cosmic web filaments that channel matter from intergalactic space into the galaxy's gravitational well. The dark matter halo also serves as a shield, protecting the galaxy from the harsh intergalactic environment. Its gravitational field can deflect or capture intergalactic gas clouds, preventing them from disrupting the galaxy's internal structure. This protective function may be crucial for maintaining the galaxy's ability to form stars over cosmic time. The study of galactic halos has revealed that visible galaxies are just the bright cores of much larger dark matter structures. This discovery has fundamentally changed our understanding of galaxy formation and evolution, suggesting that the universe's visible components represent only a small fraction of its total gravitational architecture. But this protective halo cannot shield the galaxy from the gravitational influence of its much larger neighbor, whose tidal forces are already beginning to reshape the galaxy's destiny. The Triangulum Galaxy is being slowly torn apart by invisible forces, its outer regions stretched and warped by the gravitational influence of its massive neighbor, the Andromeda Galaxy. Tidal forces, the same phenomenon that creates ocean tides on Earth, operate on galactic scales with devastating effect. The side of Triangulum closest to Andromeda experiences a stronger gravitational pull than the side farther away, creating a differential force that stretches the galaxy like cosmic taffy. This gentle but relentless stretching has been operating for billions of years, gradually reshaping the galaxy's structure. The effects are most visible in the galaxy's outer regions, where the gravitational grip is weakest. Streams of stars and gas are being pulled away from the galaxy's edges, creating tidal tails that extend far into intergalactic space. These stellar streams mark the path of Triangulum's orbit around Andromeda, like breadcrumbs dropped by a cosmic wanderer. Computer simulations reveal that Triangulum has lost a significant fraction of its original mass to tidal stripping. Stars that once belonged to the galaxy now drift in the space between galaxies, gravitationally unbound, and destined to spend eternity in the cosmic void. This ongoing mass loss is gradually reducing the galaxy's size and altering its internal dynamics. The tidal forces don't affect all parts of the galaxy equally. The central regions, where stars are more tightly bound by the galaxy's gravity, remain relatively intact. But the outer spiral arms show clear signs of distortion, with asymmetries and warping that reflect the external gravitational influence. The galaxy's once perfect spiral structure is being gradually unwound by these external forces. The interaction between Triangulum and Andromeda is not a simple two-body problem, but involves the complex gravitational dance of three major galaxies. Our own Milky Way also exerts a significant gravitational influence, creating a three-way tug-of-war that makes the system's evolution difficult to predict. The competing gravitational fields create resonances and instabilities that can dramatically alter orbital trajectories. Recent observations have detected a bridge of hydrogen gas connecting Triangulum to Andromeda, evidence of direct material transfer between the two galaxies. This gaseous umbilical cord represents matter being stripped from Triangulum and captured by its larger neighbor, a slow-motion cosmic cannibalism that will eventually consume the smaller galaxy entirely. The tidal interaction also affects star formation within Triangulum. The compression and stretching of gas clouds by tidal forces can trigger new episodes of stellar birth in some regions while suppressing it in others. This creates a complex pattern of star formation that varies across the galaxy, with some spiral arms showing enhanced activity while others appear depleted. The galaxy's dark matter halo is also being stripped by tidal forces, though this invisible mass loss is harder to detect directly. Computer models suggest that Triangulum may have lost half or more of its original dark matter halo to tidal stripping, fundamentally altering its gravitational structure and internal dynamics. As Triangulum orbits Andromeda, it experiences varying tidal forces depending on its distance from the larger galaxy. At the closest approach of its elliptical orbit, the tidal forces intensify, accelerating the stripping process and potentially triggering bursts of star formation. During more distant phases, the galaxy can partially recover, reforming some of its disrupted structure. The tidal interaction is gradually circularizing Triangulum's orbit, causing it to spiral inward toward an eventual merger with Andromeda. This process will accelerate as the galaxy loses mass and orbital energy to tidal friction, leading to an increasingly rapid decay of its orbit. The galaxy is essentially falling toward its doom, though the process will take billions of years to complete. The study of tidal interactions has revealed that galaxy evolution is not an isolated process, but involves complex gravitational relationships between neighboring systems. The local group of galaxies represents a gravitationally bound system where tidal forces play crucial roles in shaping the evolution of its member galaxies. These external influences add another layer of complexity to the already intricate story of galactic evolution, but they pale in comparison to the mysterious internal rhythms that govern the galaxy's pulse of stellar birth and death. Deep within the cosmic machinery of the Triangulum Galaxy pulses a rhythm that astronomers are only beginning to understand, a cycle of stellar birth and death that follows mysterious patterns spanning millions of years. Star formation in the galaxy is not constant but varies dramatically over time, like a cosmic heartbeat that speeds up and slows down according to some hidden conductor. During peak periods, the galaxy can produce new stars at rates 10 times higher than average, filling the spiral arms with brilliant blue giants and glowing nebulae. During quiet periods, star formation nearly ceases, leaving only the fading embers of previous stellar generations. These cycles operate on multiple timescales simultaneously. Short-term variations occur over millions of years, possibly triggered by the galaxy's passage through spiral arms or interactions with gas clouds. Longer cycles span hundreds of millions of years, potentially linked to the galaxy's orbital motion around Andromeda or encounters with other members of the local group. The triggers for these star formation cycles remain largely mysterious. One possibility is that spiral density waves create periodic compressions of the interstellar medium, squeezing gas clouds until they collapse to form stars. As the galaxy rotates, different regions pass through these compression zones, creating waves of star formation that sweep around the galactic disk like cosmic wildfire. Another potential driver is the galaxy's interaction with the cosmic web of dark matter and gas that permeates the universe. As the galaxy moves through this large-scale structure, it may encounter filaments of gas that trigger bursts of star formation when they fall into the galactic disk. These cosmic rain showers could explain some of the observed variations in star formation rates. The galaxy's magnetic field may also play a role in regulating star formation cycles. Magnetic fields can support gas clouds against gravitational collapse, preventing star formation until the field is weakened by turbulence or reconnection events. The buildup and release of magnetic pressure could create oscillating patterns of star formation across the galaxy. Internal feedback mechanisms add another layer of complexity to these cycles. Massive stars formed during intense star formation episodes produce powerful stellar winds and eventually explode as supernovas, heating the surrounding gas and potentially suppressing further star formation. This negative feedback can create boom and bust cycles where periods of intense activity are followed by relative quiescence. The chemical evolution of the galaxy also influences star formation cycles. As successive generations of stars enrich the interstellar medium with heavy elements, they change the cooling properties of the gas and the efficiency of star formation. Regions with higher metallicity may form stars more easily, while metal-poor regions may require stronger triggers to initiate collapse. Climate change on galactic scales may drive some of the longest star formation cycles. The galaxy's overall temperature and pressure can vary over cosmic time, influenced by factors such as the cosmic background radiation, the density of the local group, and the galaxy's interaction history. These changes can alter the conditions for star formation throughout the galaxy. Recent observations have revealed that star formation in Triangulum shows correlations with activity in nearby galaxies, suggesting that environmental factors operating on scales much larger than individual galaxies may influence stellar birth rates. The local group as a whole may experience coordinated cycles of star formation driven by external influences. The study of star formation histories in different regions of the galaxy reveals that these cycles are not uniform but vary from place to place. The inner regions show different patterns than the outer disk, and some spiral arms appear more active than others. This spatial variation suggests that multiple mechanisms may be operating simultaneously. Understanding these star formation cycles is crucial for predicting the galaxy's future evolution. The current star formation rate determines how long the galaxy's gas reservoirs will last and when star formation will eventually cease. These cycles also influence the galaxy's chemical evolution and the formation of planetary systems that could support life. The mystery of galactic star formation cycles represents one of the frontiers of modern astrophysics, where observations are revealing complex patterns that challenge our theoretical understanding of how galaxies work. Each cycle carries with it the legacy of countless stellar lives, enriching the cosmic environment for future generations. In the nuclear furnaces of dying stars throughout the Triangulum Galaxy, cosmic alchemists are forging the elements that will one day become planets, life forms, and perhaps even consciousness itself. When the universe began, only the three lightest elements existed: hydrogen, helium, and trace amounts of lithium. Everything else, every atom of carbon in our DNA, every molecule of oxygen we breathe, every grain of silicon in planetary crust, had to be created in the hearts of stars through nuclear fusion. The galaxy has spent 13 billion years slowly building up the periodic table, one stellar death at a time. The stellar nucleosynthesis process operates like a cosmic factory with multiple production lines. In the cores of main sequence stars like our Sun, hydrogen fuses to form helium through the proton-proton chain, releasing the energy that makes stars shine. But when these stars exhaust their hydrogen fuel, they begin burning helium to create carbon and oxygen in a process called the triple alpha reaction. More massive stars can reach higher temperatures and pressures in their cores, enabling them to forge heavier elements through successive burning stages. They burn carbon to create neon and magnesium, oxygen to create silicon and sulfur, and finally silicon to create iron peak elements. Each burning stage operates at progressively higher temperatures, reaching over 3 billion degrees in the final silicon burning phase. But stellar cores cannot create elements heavier than iron through normal fusion. These elements require the extreme conditions found only in supernova explosions, where neutron capture processes can build up heavy nuclei in seconds. The rapid neutron capture process, called the R process, creates roughly half of all elements heavier than iron, including gold, platinum, and uranium. The slow neutron capture process, called the S process, operates in the extended atmospheres of dying giant stars, gradually building up elements like strontium, barium, and lead over thousands of years. This process creates the other half of heavy elements, adding them to the stellar wind that carries material away from the dying star. The most recent addition to our understanding of stellar nucleosynthesis comes from the detection of neutron star mergers, which create kilonovae explosions that forge the heaviest elements through rapid neutron capture. These rare but violent events may be responsible for creating most of the gold and platinum in the universe, including the precious metals found on Earth. Each stellar generation adds to the galaxy's chemical inventory, gradually enriching the interstellar medium with heavier elements. The first stars were composed almost entirely of hydrogen and helium, but subsequent generations incorporated the heavy elements produced by their predecessors. This process of chemical evolution has continued for billions of years, steadily increasing the galaxy's metallicity. The distribution of heavy elements throughout the galaxy reflects its star formation history. The central regions, where star formation has been most active, show the highest abundances of heavy elements. The outer regions, where fewer generations of stars have lived and died, remain more pristine, with compositions closer to the primordial hydrogen and helium. This chemical evolution has profound implications for planet formation and the potential for life. Rocky planets like Earth can only form from material enriched with heavy elements produced by previous stellar generations. The first generation of stars could not have formed planetary systems like ours, because the necessary elements simply didn't exist yet. The galaxy's increasing metallicity also affects star formation itself. Heavy elements serve as coolants in molecular clouds, allowing them to radiate away thermal energy and collapse more efficiently. Higher metallicity gas can form stars more easily, but it also tends to produce more low-mass stars relative to high-mass ones, affecting the galaxy's overall evolution. The study of stellar abundances in different galactic regions reveals the complex mixing processes that distribute heavy elements throughout the galaxy. Supernova explosions create bubbles of hot, enriched gas that rise above the galactic disk and eventually rain back down as a galactic fountain. Stellar winds and planetary nebulae add their contributions more gently, creating a complex chemical ecosystem. Some of the most exotic elements are produced only under the most extreme conditions. Elements like technetium, which has no stable isotopes, can only be observed in the atmospheres of certain evolved stars, where they're actively being produced. These stellar laboratories create conditions that cannot be replicated on Earth, providing unique insights into nuclear physics. The ongoing chemical enrichment of the galaxy ensures that future generations of stars will have access to an even richer inventory of heavy elements. But this cosmic alchemy operates within a larger context, where galactic winds are carrying some of this precious material away from the galaxy entirely. From the Triangulum Galaxy's star-forming regions rise invisible fountains of superheated gas, carrying the galaxy's lifeblood into the cosmic void in a process that may ultimately determine its fate. Galactic winds are among the most powerful forces shaping galaxy evolution, yet they're almost entirely invisible to the naked eye. These cosmic hurricanes consist of gas heated to millions of degrees by stellar winds, supernova explosions, and shock waves from star formation. The hot gas expands rapidly, breaking free from the galaxy's gravitational grip and flowing into intergalactic space at speeds exceeding 1,000 kilometers per second. The process begins in the galaxy's most active star-forming regions, where massive stars burn through their fuel at prodigious rates. Their powerful stellar winds, moving at speeds up to 3,000 kilometers per second, collide and create superbubbles of hot gas that can grow to hundreds of light years in diameter. When these bubbles break through the galactic disk, they create chimneys that channel hot gas into the galaxy's halo. Supernova explosions add enormous amounts of energy to these outflows, heating gas to temperatures exceeding 10 million degrees and accelerating it to escape velocity. A single supernova can inject as much energy into the interstellar medium as our Sun will produce in its entire 10 billion year lifetime. In regions where multiple supernovas occur in quick succession, the combined energy can blow vast cavities in the galactic disk. These galactic winds don't just carry away mass and energy, but also transport the heavy elements forged in stellar cores. Carbon, oxygen, silicon, and iron produced by nuclear fusion are swept up in the outflows and carried into intergalactic space, where they can enrich the cosmic web and potentially seed future galaxy formation. This process represents a form of galactic pollution, contaminating the pristine hydrogen and helium of the early universe. The mass loss rate from galactic winds can be substantial, with some galaxies losing material faster than they form new stars. For the Triangulum Galaxy, computer simulations suggest that galactic winds may be removing several solar masses of material every year, gradually depleting the galaxy's gas reservoirs and reducing its future star formation potential. The winds don't escape uniformly, but follow preferred directions determined by the galaxy's structure and magnetic field. Gas tends to flow more easily perpendicular to the galactic disk, where the gravitational potential is lowest. This creates bipolar outflows that can extend thousands of light years above and below the galactic plane, forming a cosmic hourglass shape around the galaxy. The magnetic field plays a crucial role in shaping these outflows, channeling the flow of charged particles and creating complex structures within the wind. Magnetic field lines can act like cosmic highways for the escaping gas, while magnetic pressure can help accelerate the outflow and prevent it from falling back onto the galaxy. Some of the escaping gas may eventually return to the galaxy through a process called galactic recycling. Gas blown into the halo can cool and condense, eventually falling back onto the galactic disk where it can fuel new star formation. This creates a galactic fountain effect, where material cycles between the disk and halo over hundreds of millions of years. The interaction between galactic winds and the surrounding intergalactic medium creates shock waves and turbulence that can be detected by space telescopes. These observations reveal that galactic winds are not smooth, steady flows, but turbulent, chaotic phenomena with complex internal structures and time-varying properties. Different types of galaxies produce different kinds of winds. Massive galaxies with active star formation can generate powerful outflows that clear their central regions of gas, potentially quenching further star formation. Smaller galaxies like Triangulum may have weaker winds that escape more gradually, allowing continued star formation over longer timescales. The study of galactic winds has revealed that galaxies are not closed systems, but actively exchange material with their surroundings. This process is crucial for understanding galaxy evolution, as it regulates the amount of gas available for star formation and determines how long galaxies can continue to produce new stars. The ultimate fate of these winds depends on the galaxy's mass and environment. In massive galaxy clusters, the hot intracluster medium can strip away galactic winds, while isolated galaxies may retain more of their outflowing material in extended halos. For Triangulum, the presence of nearby massive galaxies like Andromeda complicates the picture, as their gravitational influence can affect the escape of galactic winds. But these departing winds pale in comparison to the cosmic catastrophe that awaits when the galaxy faces its ultimate destiny in a collision that will reshape the local group forever. In approximately 4 billion years, the Triangulum Galaxy will participate in the most spectacular collision in the local group's history, a three-way galactic merger that will forever transform our corner of the universe. The collision began billions of years ago, with the first gravitational stirrings between the Andromeda Galaxy and our own Milky Way. These two spiral giants have been approaching each other for most of cosmic history. Their mutual gravitational attraction, overcoming the expansion of the universe and drawing them together in an inexorable dance of destruction and creation. Current measurements show Andromeda approaching at over 100 kilometers per second, closing the gap between the galaxies by the width of Earth's orbit every year. This may seem slow by cosmic standards, but on the timescales of galactic evolution, it represents a headlong collision course that cannot be avoided. The merger will arrive faster than the Sun will exhaust its fuel, making it a certainty for any civilizations that might witness it. The Triangulum Galaxy finds itself caught in the middle of this cosmic catastrophe. As the third largest galaxy in the local group, it lacks the mass to significantly alter the collision between its larger neighbors, but its fate is inextricably linked to theirs. Computer simulations suggest multiple possible outcomes for Triangulum, ranging from complete destruction to survival as a satellite of the merged galaxy. The collision will not be a gentle affair. When galaxies merge, their gravitational fields interact chaotically, flinging stars into new orbits and triggering massive bursts of star formation as gas clouds collide and compress. The elegant spiral structures that define all three galaxies will be completely destroyed, their stars scattered into a new elliptical galaxy that astronomers have already nicknamed Milkomeda. For the Triangulum Galaxy, the collision represents an existential threat. Its relatively small mass makes it vulnerable to tidal disruption by the larger galaxies. Streams of stars may be torn from its outer regions and scattered throughout the merger zone, while its central core could be either destroyed or captured as a satellite of the final merged galaxy. The timing of Triangulum's involvement in the collision depends on its complex orbital motion around Andromeda. If it completes another orbit before the main collision occurs, it might escape the initial chaos only to be drawn into the merger later. If it approaches during the peak of the collision, it could be completely disrupted by the gravitational turmoil. The stellar populations of all three galaxies will be thoroughly mixed during the merger, creating a new galaxy with a complex stellar archaeology. Stars from Triangulum will find themselves orbiting alongside stars from the Milky Way and Andromeda, their original galactic identities erased by the cosmic blender of gravitational dynamics. The supermassive black holes at the centers of the merging galaxies will eventually spiral together and merge, creating gravitational waves that will ripple across the universe. This black hole merger will be one of the most energetic events in the local group's history, releasing more energy in gravitational waves than all the stars in the merged galaxy combined. The merger will also trigger the final burst of star formation in the region, as the collision compresses gas clouds and triggers gravitational collapse across vast areas. This starburst phase could make the merged galaxy one of the brightest objects in the local universe for a brief period, before the gas reserves are exhausted and star formation ceases. For any planetary systems in the region, the merger will be a time of cosmic upheaval. While direct stellar collisions will be rare due to the vast distances between stars, the changing gravitational fields could disrupt planetary orbits and send worlds into new, potentially uninhabitable trajectories. Some planets might be flung into interstellar space, while others could find themselves orbiting different stars entirely. The remnant of this cosmic collision will be a massive elliptical galaxy, roughly twice the size of the current Milky Way, but with a very different character. The new galaxy will have consumed most of the gas in the local group, leaving little material for future star formation. It will gradually fade as its stars age and die, eventually becoming a galactic graveyard of white dwarfs and stellar remnants. The merger represents not just the death of three individual galaxies, but the end of an era in the local group's evolution. The chaotic, gas-rich environment that has characterized our cosmic neighborhood for billions of years will give way to a more sedate, mature system dominated by a single massive galaxy. Yet even as this cosmic catastrophe approaches, the Triangulum Galaxy continues its ancient dance with smaller companions that trace their own orbits around its gravitational embrace. Orbiting the Triangulum Galaxy like planetary moons around a giant world are dozens of smaller galaxies, cosmic satellites that form a miniature kingdom in the vast darkness of intergalactic space. These dwarf galaxies are the Triangulum Galaxy's gravitational subjects, bound by invisible chains of dark matter and destined to follow elliptical orbits that carry them through the galaxy's extended halo. Each satellite is a galaxy in its own right, containing millions to billions of stars, but their fates are controlled by their massive overlord's gravitational influence. The largest of these cosmic companions shine with the light of hundreds of millions of stars, making them visible as faint smudges of light even from great distances. But most of Triangulum's satellites are dwarf spheroidal galaxies, so faint they were only discovered when advanced telescopes began systematically surveying the galaxy's surroundings. These galactic pygmies contain more dark matter than visible stars, making them some of the most dark matter-dominated objects in the universe. The satellite system around Triangulum tells a story of cosmic hierarchy and gravitational dominance. Computer simulations predict that every large galaxy should be surrounded by hundreds of smaller dark matter halos, but only a fraction of these halos contain enough ordinary matter to form visible stars. The satellites we can observe represent the tip of an iceberg of invisible dark matter substructure. Each satellite galaxy follows its own unique orbital path, some taking hundreds of millions of years to complete a single revolution around Triangulum. The closest satellites experience strong tidal forces that can strip away their outer stars, creating stellar streams that trace their orbital paths like cosmic breadcrumbs. These tidal streams provide direct evidence of the ongoing gravitational interaction between the satellites and their host galaxy. The satellite galaxies are not passive objects, but active participants in the galaxy's evolution. As they orbit through Triangulum's halo, they can trigger gravitational resonances that affect the host galaxy's structure. Their gravitational influence can heat the galactic disk, thicken spiral arms, and potentially influence star formation rates in different regions. Some satellites are gradually being consumed by their host galaxy through tidal disruption. Over billions of years, repeated passages through the galaxy's gravitational field strip away their stars, eventually leaving only their central dark matter cores. The disrupted stellar material becomes part of the galaxy's extended halo, adding to its stellar population and altering its chemical composition. The diversity of satellite galaxies around Triangulum reflects different formation histories and environments. Some formed early in cosmic history when gas densities were higher, creating relatively metal-rich stellar populations. Others formed more recently from gas that had been previously heated and ionized, resulting in smaller, more metal-poor systems. Star formation in satellite galaxies is often suppressed by environmental effects. The hot halo gas around Triangulum can strip away the cool gas needed for star formation through a process called ram pressure stripping. Additionally, the galaxy's ultraviolet radiation can ionize and heat gas in nearby satellites, preventing it from cooling and collapsing to form new stars. The study of satellite galaxies has revealed important constraints on dark matter physics. The number, distribution, and properties of satellites depend on the nature of dark matter particles and the way structure forms in the universe. Comparing observations with computer simulations helps test different dark matter models and refine our understanding of cosmic evolution. Some of Triangulum's satellites may themselves have smaller companions, creating a hierarchical system of galaxies within galaxies. These sub-satellite systems are extremely difficult to detect, but may be common throughout the universe, representing another level of cosmic structure. The satellite system around Triangulum is not stable over cosmic time. Dynamical friction causes the most massive satellites to spiral inward, eventually merging with the host galaxy. Meanwhile, tidal interactions with other local group galaxies can strip away satellites or alter their orbits, gradually eroding the satellite population. The ultimate fate of Triangulum satellites depends on the upcoming merger with Andromeda and the Milky Way. Some satellites may be flung into intergalactic space by the gravitational chaos, while others could find themselves captured by one of the merging giants. The collision will scatter this cosmic cord across vast distances, ending billions of years of gravitational partnership. As we survey this galactic kingdom and its loyal subjects, we're witnessing a cosmic hierarchy that extends from the largest scales of dark matter structure down to individual stars and planets. The satellite galaxies of Triangulum represent stepping stones in the cosmic web, connecting the galaxy to the larger universe and hinting at the vast structures that shape our cosmic destiny. Invisible to our eyes but detectable by the most sensitive instruments ever built, gravitational waves are constantly washing through the Triangulum Galaxy, carrying messages from some of the most violent events in cosmic history. These ripples in spacetime itself are created when massive objects accelerate through the universe's gravitational field. Every orbiting binary star system, every colliding black hole. Every exploding supernova sends gravitational waves racing across the cosmos at the speed of light. The galaxy exists within an ocean of these space-time distortions, each wave carrying information about distant cosmic catastrophes. The most powerful gravitational wave sources are the mergers of compact objects like neutron stars and black holes. When two neutron stars spiral together and collide, they create gravitational waves so strong they can be detected from billions of light years away. These cosmic crashes occur perhaps once every few 100,000 years in a galaxy like Triangulum, but the waves they produce ripple outward for eternity. The waves themselves represent a fundamental prediction of Einstein's general relativity, the stretching and compression of space and time by accelerating masses. As a gravitational wave passes through the galaxy, it alternately stretches and compresses distances by amounts smaller than 1,000th the width of a proton. This incredibly tiny effect can only be detected by laser interferometry experiments that measure changes in the length of kilometer-scale baselines. The discovery of gravitational waves has opened an entirely new window onto the universe, allowing astronomers to detect events that produce no light at all. Binary black hole mergers, which were previously invisible to traditional telescopes, now announce themselves through the characteristic chirp of gravitational waves as the orbiting objects spiral together faster and faster before final collision. Within the Triangulum Galaxy, dozens of known binary systems are slowly losing energy to gravitational wave emission, causing their orbits to decay over millions of years. The most famous example is a binary pulsar system, where one neutron star acts as a cosmic lighthouse, sweeping beams of radio waves across space with clockwork precision. The gradual speed-up of this orbital dance matches Einstein's predictions exactly. The galaxy's supermassive black hole mergers, which occurred during its formation billions of years ago, would have created some of the most powerful gravitational wave events in cosmic history. These early mergers helped shape the galaxy's central structure and may have ejected smaller black holes through gravitational recoil effects, creating the population of wandering black holes that roam the galaxy today. Gravitational waves also carry information about the expansion history of the universe. By measuring both the wave amplitude and the redshift of their sources, astronomers can determine cosmic distances without relying on traditional distance indicators. This makes gravitational wave astronomy a powerful tool for studying dark energy and the acceleration of cosmic expansion. The waves propagate through matter almost unimpeded, passing through stars, planets, and entire galaxies as if they weren't there. This means that gravitational wave signals preserve information about their sources with extraordinary fidelity, providing clean measurements of masses, spins, and orbital parameters that would be impossible to obtain through electromagnetic observations alone. Future space-based gravitational wave detectors will be sensitive to lower frequency waves produced by massive black hole mergers and galactic binary systems. These instruments will be able to detect every white dwarf binary in the Milky Way and track the population of massive black hole pairs throughout the observable universe. The constant bombardment of gravitational waves may also have subtle effects on the galaxy's structure and evolution. While individual waves are extremely weak, the cumulative effect of billions of years of gravitational wave radiation may influence the dynamics of stellar systems and the evolution of binary populations. Some theoretical models suggest that gravitational waves could even affect the formation of planetary systems, influencing the migration of planets in binary star systems, or altering the dynamics of asteroid belts and comet clouds. These effects would be extraordinarily small, but could accumulate over cosmic time. The study of gravitational waves from the Triangulum Galaxy and its neighbors is revealing the hidden violence of the cosmos, events so energetic they shake the very fabric of space-time itself. These ripples connect every object in the universe through the fundamental geometry of space and time, creating a cosmic communication network that has operated since the beginning of time itself. But to truly understand the galaxy's place in cosmic history, we must look even deeper, to the ancient light that still carries information from the universe's earliest moments. Every photon of light from the Triangulum Galaxy carries within it a timestamp from the past, creating a cosmic archaeological record that allows us to witness the galaxy's evolution across billions of years of cosmic history. Light takes time to travel through space, turning every astronomical observation into a journey back in time. The light from Triangulum's core that reaches us tonight began its journey 3 million years ago, when early humans were first walking upright on Earth. More distant regions of the galaxy show us even earlier epochs, creating a time machine that reveals how the galaxy has changed over cosmic history. The galaxy's oldest stars preserve information from the universe's youth, when heavy elements were scarce and star formation proceeded under very different conditions than today. These ancient stellar populations contain chemical signatures from the first generation of massive stars, which lived fast, died young, and enriched the early universe with the first heavy elements beyond hydrogen and helium. By studying stars of different ages throughout the galaxy, astronomers can reconstruct its star formation history, tracing periods of intense stellar birth triggered by galactic mergers or gas infall events. The chemical abundances of these stellar populations reveal how the galaxy gradually enriched itself with heavy elements over billions of years of stellar evolution. The most distant galaxies visible to our telescopes show us cosmic conditions from over 13 billion years ago, when the universe was less than 1 billion years old. These early galaxies were smaller, more irregular, and had higher rates of star formation than modern spiral galaxies like Triangulum. They represent the building blocks from which today's massive galaxies were assembled through mergers and accretion. The Hubble Space Telescope and other deep-field observations have revealed that the early universe was filled with small, star-forming galaxies that gradually merged to form larger systems. The Triangulum Galaxy likely formed through the merger of dozens of these early galaxy fragments, each contributing its stars and gas to the growing system. Ancient light also reveals periods when the galaxy experienced major disruptions. Stellar streams and tidal tails preserve evidence of past galactic encounters, their stars carrying chemical signatures and kinematic information that reveals when and how these interactions occurred. Some of these disrupted systems may be the remnants of satellite galaxies that were completely torn apart by tidal forces. The galaxy's globular clusters serve as stellar time capsules, preserving populations of stars that formed during specific epochs in galactic history. The ages and chemical compositions of these clusters reveal periods of intense star formation that may have been triggered by major merger events or episodes of gas accretion from the cosmic web. Even the galaxy's dark matter halo contains information about its formation history. Computer simulations suggest that the halo formed through the gradual accumulation of smaller dark matter clumps, each leaving subtle signatures in the halo's density profile and substructure. These dark matter fossils can be detected through their gravitational effects on stellar streams and satellite galaxies. The cosmic microwave background radiation provides a snapshot of the universe when it was only 380,000 years old, long before the first stars formed. Tiny temperature fluctuations in this ancient light reveal the density variations that eventually grew into galaxies like Triangulum through gravitational amplification over cosmic time. Observations of quasars and other distant active galactic nuclei show us how supermassive black holes grew and influenced galaxy evolution in the early universe. The Triangulum Galaxy's lack of a central supermassive black hole suggests it may have had a different evolutionary history than galaxies that experienced more violent growth phases. The study of ancient light has revealed that galaxy formation is an ongoing process rather than a single event. Galaxies continue to accrete gas from the cosmic web, experience mergers with smaller systems, and evolve their stellar populations over cosmic time. The Triangulum Galaxy we observe today is still growing and changing, shaped by the same processes that have operated since its formation. Looking forward, next-generation telescopes will be able to observe even more distant galaxies, potentially seeing the very first stellar populations that formed in the universe. These observations will reveal how galaxies like Triangulum emerged from the cosmic dark ages and began the process of stellar nucleosynthesis that has enriched the universe with heavy elements. The ancient light from cosmic dawn continues to rain down on us today, carrying information about events that occurred billions of years before Earth existed. Each photon is a messenger from the deep past, preserving the memory of cosmic evolution in the quantum structure of electromagnetic radiation. But even as we trace the galaxy's history through ancient light, A mysterious force is reshaping the cosmic architecture around us, driving the universe toward an uncertain future. Surrounding the Triangulum Galaxy and permeating every cubic centimeter of space is a mysterious force that is tearing the universe apart, accelerating the expansion of space itself and driving galaxies away from each other at ever-increasing speeds. Dark energy represents the most profound mystery in modern cosmology, an unknown form of energy that makes up roughly 70% of the universe, but whose nature remains completely enigmatic. Unlike dark matter, which clumps together gravitationally, dark energy appears to be smoothly distributed throughout space, exerting a constant pressure that acts like anti-gravity on cosmic scales. The discovery of cosmic acceleration came from observations of distant supernovas, stellar explosions so consistent in their brightness that they serve as cosmic standard candles. When astronomers measured the distances to these exploding stars, they found that the most distant ones appeared fainter than expected, indicating that the expansion of the universe has been speeding up over the past several billion years. This acceleration defies our intuitive understanding of gravity and cosmic evolution. After the Big Bang, the mutual gravitational attraction of all matter in the universe should have gradually slowed the expansion, possibly even reversing it in a cosmic collapse. Instead, the expansion began accelerating roughly 5 billion years ago when dark energy's influence overcame the gravitational pull of matter. For galaxies within the local group, including Triangulum, dark energy's effects are currently negligible compared to their mutual gravitational attraction. The local group remains gravitationally bound and will continue to evolve through mergers and interactions regardless of cosmic acceleration. But on larger scales, dark energy is already having dramatic effects on the universe's structure. Galaxy clusters beyond the local group are being carried apart by cosmic expansion faster than light can travel between them. In the far future, these distant galaxies will disappear beyond our cosmic horizon, their light redshifted to such long wavelengths that they become effectively invisible. The observable universe will gradually shrink to include only the local group and its immediate neighbors. The nature of dark energy remains one of the greatest unsolved problems in physics. One possibility is that it represents the energy of empty space itself, a quantum phenomenon called vacuum energy. But calculations of vacuum energy from particle physics predict values that are vastly larger than what we observe, creating a discrepancy of more than 100 orders of magnitude. Another possibility is that dark energy is a dynamic field that changes over time, similar to the inflaton field thought to have driven cosmic inflation in the early universe. This quintessence field could have different properties at different times, potentially explaining why dark energy only began to dominate the universe relatively recently in cosmic history. Some theories propose modifications to Einstein's general relativity that could explain cosmic acceleration without invoking dark energy. These modified gravity theories suggest that gravity behaves differently on cosmic scales than it does in the solar system, creating apparent acceleration without requiring a new form of energy. The future evolution of dark energy will determine the ultimate fate of the universe. If dark energy remains constant, the universe will continue expanding forever, gradually cooling and diluting until all the stars burn out and only black holes remain. If dark energy increases over time, it could eventually overcome all other forces, tearing apart galaxies, stars, and even atoms in a cosmic event called the Big Rip. Measurements of cosmic acceleration using different techniques all point to the same conclusion. The universe's expansion is speeding up, driven by some form of energy that permeates all of space. Observations of galaxy clusters, gravitational lensing, and the cosmic microwave background all provide independent confirmation of dark energy's existence. The local group's isolation in an accelerating universe has profound implications for the future of astronomy. Billions of years from now, astronomers in the merged Milky galaxy will see a much emptier universe, with only a few nearby galaxies visible in their night sky. The rich cosmic web of galaxy clusters and filaments that we observe today will have disappeared beyond their cosmic horizon. For civilizations that might arise in the far future, the evidence for the Big Bang and cosmic evolution will be much harder to find. They will inhabit a cosmic island, isolated from the rest of the universe by the accelerating expansion of space itself. The cosmic microwave background will have cooled and redshifted beyond detection, erasing one of our most important clues about the universe's origin. The study of dark energy represents the frontier of cosmology, where observations are revealing phenomena that challenge our most fundamental understanding of space, time, and gravity. As we continue to probe this cosmic mystery, we may discover that our universe is even stranger and more wonderful than we currently imagine. Yet even as dark energy reshapes the cosmic future, the elegant structures we see today may themselves be more fragile than they appear. The elegant spiral arms that define the Triangulum Galaxy's beauty may be nothing more than a temporary cosmic pattern, destined to fade and reform in an endless cycle of creation and destruction that operates over hundreds of millions of years. Spiral structure represents one of the most persistent puzzles in galactic astronomy. If the spiral arms were simply material features rotating with the galaxy, they would wind up completely after just a few rotations, creating a tightly coiled spring rather than the open, elegant patterns we observe. The fact that spiral galaxies maintain their structure over billions of years suggests that something more complex is at work. The current understanding of spiral structure treats the arms as transient waves rather than permanent features. These spiral density waves propagate through the galactic disk like ripples on a cosmic pond, compressing gas and triggering star formation as they pass. The bright young stars that illuminate the spiral arms are not permanent residents but temporary markers of these passing compression waves. Computer simulations reveal that spiral patterns can be remarkably dynamic, strengthening and weakening over cosmic timescales. Some models suggest that spiral arms can form spontaneously from gravitational instabilities in the galactic disk, grow to prominence over tens of millions of years, then fade away as the driving instabilities dissipate. New spiral patterns can emerge from different instabilities, creating a constantly evolving galactic architecture. The number of spiral arms in a galaxy can change over time. Triangulum currently displays a two-armed spiral pattern, but this may not be its permanent configuration. Gravitational interactions with neighboring galaxies, the passage of massive gas clouds, or internal instabilities could alter the arm number and pattern, transforming the galaxy's appearance over cosmic time. The spiral pattern may also be influenced by the galaxy's bar structure, though Triangulum appears to lack the prominent central bar seen in many spiral galaxies. Computer models show that bars can drive spiral waves, creating and maintaining arm patterns through gravitational torques. The absence of a strong bar in Triangulum suggests that its spiral structure may be maintained by other mechanisms or may be less stable than in strongly barred galaxies. Recent observations have revealed that many galaxies show evidence of multiple spiral patterns operating simultaneously, with different arm segments having different pitch angles and rotation speeds. This suggests that spiral structure may be more complex and chaotic than simple density wave theory predicts, with multiple overlapping patterns creating the observed morphology. The interaction between spiral arms and stellar feedback processes adds another layer of complexity. Massive star formation in spiral arms produces stellar winds and supernova explosions that can disrupt the very density enhancements that created the arms. This feedback can weaken spiral patterns over time, potentially erasing them entirely in regions of intense star formation. Environmental factors also influence spiral structure stability. Galaxies in dense clusters often lose their spiral patterns through interactions with the intracluster medium and neighboring galaxies. Triangulum's location in the relatively sparse local group may have helped preserve its spiral structure, but the upcoming merger with Andromeda and the Milky Way will certainly destroy its current pattern. The study of spiral galaxies at different redshifts has revealed that spiral patterns were less common in the early universe, when galaxies were smaller, more irregular, and had higher rates of mergers and interactions. This suggests that spiral structure may be a relatively recent development in cosmic history, emerging as galaxies settled into more stable configurations. Some theoretical models propose that spiral patterns undergo regular cycles of formation and dissolution, driven by the galaxy's rotation and internal dynamics. These cycles could operate on timescales of hundreds of millions of years, meaning that the spiral pattern we observe today may be just one phase in a long-term oscillation. The magnetic field structure in spiral galaxies often follows the spiral pattern, suggesting a close connection between magnetic and gravitational forces in maintaining arm structure. Changes in the magnetic field configuration could potentially trigger the formation of new spiral patterns or the destruction of existing ones. Future observations with next-generation telescopes may be able to detect temporal changes in spiral structure by comparing high-resolution images taken decades apart. These measurements could reveal how quickly spiral patterns evolve and whether they follow predictable cycles or exhibit more chaotic behavior. The temporary nature of spiral structure highlights the dynamic character of galaxy evolution. The beautiful patterns we see in the night sky are not eternal sculptures, but fleeting arrangements of matter and energy, constantly reshaping themselves through the interplay of gravity, star formation, and cosmic environment. As we admire the Triangulum Galaxy's elegant spiral arms, we're witnessing a cosmic moment frozen in time, a particular configuration in an ongoing dance of matter and energy that will continue long after the pattern itself has dissolved into cosmic history. But even as galactic structures evolve and transform, they exist within an ocean of ancient radiation that has bathed the universe since its earliest moments. Every cubic centimeter of space surrounding the Triangulum Galaxy is filled with ancient photons from the universe's infancy, a cosmic background radiation that carries within it the fossilized imprint of creation itself. The cosmic microwave background represents the oldest light in the universe, photons that began their journey when the cosmos was only 380,000 years old. At that moment, the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms, making space transparent for the first time since the Big Bang. The brilliant flash of this cosmic dawn has been traveling through space ever since, gradually cooling and stretching to microwave wavelengths. This ancient radiation bathes the Triangulum Galaxy from all directions with nearly perfect uniformity, maintaining a temperature of just 2.7 degrees above absolute zero. The photons carry no memory of their 13 billion-year journey through space, arriving at Earth with the same intensity they had when atoms first formed in the primordial universe. Yet within this seemingly uniform background lie tiny temperature fluctuations, variations of just a few millionths of a degree that represent the seeds from which all cosmic structure grew. These quantum ripples in the early universe, stretched to cosmic proportions by inflation, provided the gravitational wells around which the first dark matter halos formed, eventually giving birth to galaxies like Triangulum. The cosmic microwave background serves as a cosmic baby picture, showing us the universe when it was smooth, hot, and filled with a nearly uniform plasma of protons, electrons, and photons. The slight density variations visible in this ancient light reveal the initial conditions from which 13 billion years of cosmic evolution would unfold. Every galaxy in the universe moves through this background radiation field, creating a slight Doppler shift that reveals cosmic motion on the largest scales. The Triangulum Galaxy, along with the entire local group, is moving at over 600 kilometers per second relative to the cosmic microwave background, carried along by the gravitational influence of massive structures in the cosmic web. This motion creates a dipole pattern in the background radiation, with photons appearing slightly hotter in the direction of motion and cooler in the opposite direction. This cosmic speedometer allows astronomers to measure the local group's motion through the universe and map the large-scale gravitational fields that drive this cosmic flow. The polarization of the cosmic microwave background provides additional information about the early universe, revealing how photons scattered off electrons in the primordial plasma. These polarization patterns carry signatures of gravitational waves from cosmic inflation, potentially providing direct evidence for the rapid expansion that occurred in the universe's first fraction of a second. As the universe continues to expand, the cosmic microwave background grows steadily colder and fainter. In the far future, this ancient radiation will cool to such low temperatures that it becomes virtually undetectable, erasing one of our most important windows into cosmic history. Future civilizations may lose access to this crucial evidence for the Big Bang and early cosmic evolution. The background radiation also provides a fundamental reference frame for the universe, defining a cosmic rest frame relative to which all motion can be measured. This frame is particularly important for understanding dark energy and cosmic acceleration, as it provides a standard against which the expansion history of the universe can be measured. Subtle interactions between galaxies and the cosmic microwave background can heat the radiation through inverse Compton scattering, creating slight temperature increases in regions where hot gas is present. These thermal signatures allow astronomers to map the distribution of hot gas throughout the universe and study the evolution of galaxy clusters. The cosmic microwave background has been measured with extraordinary precision by satellite missions, revealing the universe's geometry, composition, and history with unprecedented accuracy. These measurements have confirmed that the universe is flat, composed of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. Future observations of the cosmic microwave background may reveal even more subtle effects, including signatures of cosmic strings, primordial black holes, or other exotic phenomena from the early universe. Each new measurement adds to our understanding of the fundamental physics that govern cosmic evolution. The ancient photons of the cosmic microwave background connect every object in the universe to its common origin in the Big Bang. As they stream through the Triangulum Galaxy, they carry with them the memory of a time before stars, before galaxies, before any of the cosmic structures we see today existed. This radiation represents the universe's most ancient light, a cosmic heritage that links us to the very moment when space became transparent and the cosmos began its long journey toward the rich, complex universe we inhabit today. But even this ancient radiation originated from earlier quantum fluctuations that seeded the entire cosmic architecture we observe around us. The Triangulum Galaxy owes its existence to quantum uncertainty, born from microscopic fluctuations in the fabric of space-time that occurred when the universe was smaller than a single atom. In the first fraction of a second after the Big Bang, the entire observable universe was compressed into a region smaller than a proton, governed by the strange laws of quantum mechanics, where particles and energy exist in states of fundamental uncertainty. At these scales, the very notion of empty space breaks down, replaced by a seething foam of virtual particles and energy fluctuations that appear and disappear on timescales too brief to measure. These quantum fluctuations represented tiny variations in energy density, random patterns of slightly more and slightly less dense regions scattered throughout the primordial universe. Under normal circumstances, these microscopic ripples would have remained forever invisible, too small to influence the macroscopic world. But the universe was about to undergo a transformation that would amplify these quantum whispers into cosmic shouts. Cosmic inflation, a period of exponential expansion, lasting perhaps 10 to the minus 35 seconds, stretched these quantum fluctuations to astronomical scales. Regions that were once separated by distances smaller than the width of a proton suddenly found themselves separated by light years. The tiny energy variations that existed on quantum scales became density fluctuations spanning vast cosmic volumes. When inflation ended, these amplified quantum fluctuations provided the seeds for all future cosmic structure. Regions that were slightly denser than average had stronger gravitational fields, allowing them to attract additional matter and grow even denser over time. This process of gravitational amplification operated over billions of years, transforming tiny quantum ripples into galaxies, galaxy clusters, and the cosmic web itself. The Triangulum Galaxy began as one of these quantum fluctuations, a microscopic density enhancement that existed when the universe was incomprehensibly young and small. The matter that would eventually form its hundreds of billions of stars was initially spread over a vast region of space, held together only by the gravitational memory of that primordial quantum fluctuation. Computer simulations can trace the evolution of individual quantum fluctuations from the end of inflation to the present day, showing how microscopic variations in the early universe grew into the massive structures we observe today. Each galaxy represents the culmination of nearly 14 billion years of gravitational evolution, all tracing back to quantum uncertainty in the universe's first moment. The statistical properties of these quantum fluctuations have been precisely measured through observations of the cosmic microwave background, revealing that they follow a nearly scale-invariant spectrum predicted by inflation theory. This remarkable agreement between quantum mechanics and cosmological observations provides strong evidence that our understanding of the early universe is fundamentally correct. Different types of quantum fluctuations may have contributed to cosmic structure formation. Scalar field fluctuations, associated with the inflaton field that drove cosmic expansion, created the density variations that became galaxies and galaxy clusters. Tensor fluctuations, representing gravitational waves from the inflationary epoch, may have left their signatures in the polarization patterns of the cosmic microwave background. The quantum origin of cosmic structure connects the smallest scales of physics to the largest scales of astronomy, demonstrating that quantum mechanics is not just a laboratory curiosity, but a fundamental principle that shapes the entire universe. The galaxy we inhabit exists because of the inherent uncertainty built into the quantum vacuum itself. Some theories suggest that the multiverse concept may emerge naturally from quantum fluctuations during inflation, with different regions of space experiencing different amounts of expansion and ending up with different physical properties. In this view, our observable universe may be just one bubble in an infinite cosmic foam of parallel universes. The study of cosmic structure formation has revealed that dark matter played a crucial role in amplifying these quantum fluctuations. Without dark matter's gravitational scaffolding, the small density variations left over from inflation would not have been able to grow large enough to form galaxies before the universe's expansion diluted them away. Recent observations of the early universe with space telescopes are beginning to see the first galaxies that formed from these quantum seeds, revealing how cosmic structure emerged from the smooth background left over from the Big Bang. These observations provide direct tests of our understanding of how quantum fluctuations evolved into the cosmic web. The quantum fluctuations that seeded galaxy formation also determined the statistical properties of cosmic structure on all scales. The clustering of galaxies, the shapes of cosmic voids, and the filamentary structure of the cosmic web all trace back to the random quantum processes that operated in the universe's first moment. As we contemplate the Triangulum Galaxy and its place in the cosmic web, we're witnessing the ultimate expression of quantum mechanics writ large across the cosmos. Every star, every planet, every living thing owes its existence to the fundamental uncertainty that governs reality at its deepest level. The quantum fluctuations that created our galaxy also embedded it within a vast network of cosmic structure that extends across billions of light years. The Triangulum Galaxy does not exist in isolation but is embedded within the largest structure in the universe, a cosmic web of dark matter filaments that connects galaxies across billions of light years in an intricate network of matter and energy. This cosmic web represents the universe's fundamental architecture, a three-dimensional scaffolding built from dark matter that formed over billions of years of gravitational evolution. Like a vast spider web stretched across space, the cosmic web consists of dense filaments separated by enormous voids, creating a foam-like structure that extends throughout the observable universe. The filaments themselves are highways of dark matter and gas that channel material from the cosmic voids into dense nodes where galaxies form and evolve. These cosmic arteries can stretch for hundreds of millions of light years, connecting distant galaxy clusters in a network that spans scales larger than any single astronomical object. The Triangulum Galaxy sits within one of these filaments, part of the local group's position in a relatively dense region of the cosmic web. The gravitational influence of this large-scale structure has shaped the local group's evolution, determining which galaxies became gravitationally bound and how they have interacted over cosmic time. Galaxy formation within the cosmic web follows a hierarchical pattern, with the largest structures forming at the intersections of multiple filaments. These cosmic crossroads become the sites of massive galaxy clusters, gravitational wells so deep they can trap thousands of galaxies and vast quantities of hot gas. The local group occupies a more modest position in this hierarchy, located along a smaller filament rather than at a major intersection. The cosmic web's filamentary structure traces the underlying dark matter distribution, which began forming shortly after the Big Bang, when tiny density fluctuations in the early universe began to grow under their own gravity. Over billions of years, these fluctuations evolved into a network of dark matter halos connected by streams of matter flowing along the web's filaments. Gas follows the dark matter, flowing along filaments toward the dense nodes where galaxies form. This cosmic plumbing system has operated throughout the universe's history, feeding galaxies with the raw materials needed for continued star formation. When gas flows along, filaments are disrupted or cut off, galaxies can become starved of fuel and cease forming new stars. The cosmic web also determines galaxy properties through environmental effects. Galaxies in dense filaments and cluster cores experience ram pressure stripping, tidal interactions, and other processes that can remove their gas and halt star formation. Galaxies in cosmic voids, far from major filaments, may evolve in relative isolation with different star formation histories. Computer simulations reveal that the cosmic web has a fractal-like structure, with smaller filaments branching off from larger ones in a hierarchy that extends down to galactic scales. This self-similar structure emerges naturally from gravitational collapse and reflects the scale-invariant nature of the initial quantum fluctuations that seeded cosmic structure. The local group's motion through the cosmic web is influenced by the gravitational pull of massive structures like the Virgo cluster and the Great Attractor, enormous concentrations of matter that exert their influence across hundreds of millions of light-years. This cosmic flow carries the local group at speeds exceeding 600 kilometers per second relative to the cosmic microwave background. Dark energy's acceleration of cosmic expansion is gradually stretching the cosmic web, making filaments longer and thinner while enlarging the cosmic voids. This process will eventually disconnect distant parts of the web, isolating galaxy groups like the local group from the larger cosmic structure as space itself expands between them. The study of the cosmic web has revealed that most of the universe's ordinary matter exists not in galaxies but in the warm, hot intergalactic medium that fills the filaments. This tenuous plasma, heated to millions of degrees by structure formation processes, contains roughly half of all the ordinary matter in the universe, but is extremely difficult to detect directly. Observations of distant quasars and other background sources can reveal the cosmic web through absorption lines created by intervening gas along the filaments. These observations show that the web extends to the highest redshifts observable, indicating that large-scale structure formation began very early in cosmic history. The cosmic web also influences the spin orientations of galaxies, with some studies suggesting that galaxies tend to align their rotation axes with nearby filaments. This cosmic choreography reflects the way that tidal torques from large-scale structure can influence galaxy formation and evolution. Future surveys will map the cosmic web in unprecedented detail, revealing how dark matter, gas, and galaxies are distributed throughout the universe. These observations will test our understanding of structure formation and dark energy, providing new insights into the fundamental forces that shape cosmic evolution. The Triangulum Galaxy's position within this vast network connects it to the entire observable universe, making it part of a cosmic community that extends far beyond our local group. The web that surrounds us represents the universe's grandest architecture, a structure so vast that light takes billions of years to traverse its largest features. As we continue our journey through this cosmic web, we approach questions about the ultimate fate of all the structures we have encountered, including the galaxies themselves. Across the next 100 trillion years, every star in the Triangulum Galaxy will live out its destined evolution, transforming the cosmos from a brilliant tapestry of stellar light into a graveyard of cooling remnants drifting through an ever-expanding darkness. The stellar era that has defined the universe for the past 13 billion years represents just the opening chapter in cosmic history. The most massive stars in Triangulum, those brilliant blue giants that burn with the intensity of millions of suns, will exhaust their fuel first. Within just a few million years, they will explode as supernovas or collapse into black holes, adding to the galaxy's growing population of stellar corpses. Medium-mass stars like our Sun face a different fate, burning steadily for billions or even trillions of years before swelling into red giants and finally shedding their outer layers as planetary nebulae. The white dwarf cores they leave behind will shine with stored thermal energy for tens of billions of years, gradually cooling from white-hot to red, then brown, then black as they radiate their heat into the cosmic void. The smallest stars, red dwarfs with masses less than half that of our Sun, will outlive all others. These cosmic misers burn their hydrogen fuel so slowly that they can maintain nuclear fusion for over 100 trillion years, thousands of times longer than the current age of the universe. They will be the last stars shining when the galaxy finally goes dark. As stellar evolution proceeds, the galaxy's character will change dramatically. The brilliant blue and white stars that currently illuminate the spiral arms will vanish first, leaving behind populations increasingly dominated by cooler, redder stars. The galaxy's overall brightness will fade steadily, as its most luminous members burn out and are not replaced. Star formation itself will gradually cease as the galaxy exhausts its reserves of star-forming gas. Stellar winds, supernova explosions, and galactic outflows will blow away much of the remaining interstellar medium, while the rest will be locked up in long-lived stars, or stellar remnants. Without new stars being born, the galaxy will begin its slow fade into darkness. The merger with Andromeda and the Milky Way will accelerate this process by triggering a final burst of star formation that quickly consumes the remaining gas reservoirs. The resulting elliptical galaxy will have few young stars and little ongoing star formation, representing the end of the galaxy's active phase of stellar birth and evolution. Over cosmic time, even the longest-lived stars will eventually die. When the last red dwarf finally exhausts its fuel in the far future, the stellar era will end, replaced by an epoch dominated by brown dwarfs, white dwarfs, neutron stars, and black holes. These stellar remnants will continue to interact gravitationally, but they will no longer produce the nuclear fusion that has powered cosmic evolution for eons. Brown dwarfs, failed stars that never achieved the temperatures needed for sustained nuclear fusion, will experience a brief moment of glory as the universe cools around them. These cosmic embers may actually become warmer than their surroundings for a time, making them some of the most active objects in the post-stellar universe. White dwarf stars will undergo their own slow evolution, crystallizing into cosmic diamonds as they cool over trillions of years. Some white dwarfs in binary systems may experience thermonuclear explosions when they accrete matter from companions, creating brief supernovas in an otherwise dark galaxy. These events will become increasingly rare as binary systems evolve and separate. Neutron stars will continue their cosmic lighthouse behavior, sweeping beams of radiation across space as they rotate, but even these will eventually slow down and fade as their rotational energy dissipates. The radio pulsars that currently serve as cosmic timekeepers will gradually fall silent, their beams weakening until they can no longer be detected. Black holes will become increasingly dominant as other objects fade. They will continue to grow by accreting matter and merging with each other, creating ever more massive black holes that will ultimately dominate the galaxy's gravitational field. These cosmic vacuum cleaners will slowly consume the galaxy's remaining matter over timescales that dwarf even the stellar era. The process of stellar evolution will also be influenced by the expanding universe itself. As space continues to expand under the influence of dark energy, the galaxy will become increasingly isolated from its cosmic environment. The background temperature of the universe will continue to drop, eventually falling below the temperature of the coolest stellar remnants. In this far future, the distinction between hot and cold will reverse. Black holes, which currently appear cold against the cosmic background, will eventually become the warmest objects in the universe as everything else cools toward absolute zero. Their Hawking radiation, currently undetectable, will become the primary source of energy in a universe that has otherwise reached thermal equilibrium. The end of stellar evolution marks not just the death of individual stars, but the conclusion of the universe's most vibrant and creative epoch. The stellar era has given birth to heavy elements, planetary systems, and potentially life itself. When it ends, the universe will enter a much longer and quieter phase of its evolution. Yet even as the stars fade and die, the universe itself faces an even more fundamental transformation that will determine the ultimate fate of matter and energy on the largest scales. In the unimaginably distant future, the Triangulum Galaxy and all cosmic structures will succumb to the inexorable march toward maximum entropy, dissolving into a universe of perfect equilibrium where no energy flows and no processes can occur. The heat death of the universe represents the ultimate expression of the second law of thermodynamics on cosmic scales. Just as a hot cup of coffee inevitably cools to match room temperature, the universe is gradually evolving toward a state where all matter and energy reach the same temperature and no further work can be performed. This cosmic equilibrium will mark the end not just of stars and galaxies, but of time itself as a meaningful concept. The journey toward heat death begins with the accelerating expansion driven by dark energy. As space continues to expand exponentially, galaxies will be carried apart faster than light can travel between them. The observable universe will shrink to encompass only the local group and its immediate neighbors, creating cosmic islands of matter separated by vast expanses of empty space. Within these isolated regions, gravity will continue to operate, gradually pulling matter together into increasingly massive black holes. Stars will be torn apart by tidal forces as they spiral into these cosmic drains, while planets and asteroids will follow similar fates over unimaginably long timescales. Eventually, each galactic remnant will collapse into a single supermassive black hole containing all the matter that once formed billions of stars. But even black holes are not eternal. According to Stephen Hawking's theoretical calculations, black holes slowly evaporate through quantum effects at their event horizons, emitting radiation and gradually losing mass over timescales that dwarf the current age of the universe. A black hole with the mass of our Sun would take longer than 10 to the 67th power years to evaporate completely, a time so vast that it defies human comprehension. The supermassive black holes that will eventually consume entire galaxies will persist even longer, their evaporation times extending to 10 to the 100 power years or more. During this unthinkably long epoch, these black holes will be the only remaining sources of energy in an otherwise dead universe, slowly radiating their mass away as Hawking radiation until nothing remains. As black holes evaporate, they will populate the universe with a thin soup of elementary particles, photons, and neutrinos. These particles will spread throughout the expanding space, their density decreasing as the universe grows larger and larger. Eventually, the expansion will carry particles so far apart that they rarely interact, creating a cosmos of infinite size but negligible density. The temperature of this final state will approach absolute zero, limited only by the cosmic microwave background radiation that will continue to cool as the universe expands. In this cold, dark future, no complex structures can form or persist. There will be no stars, no planets, no life, and no observers to witness the cosmic silence. Even protons, the building blocks of atomic nuclei, may not survive forever. Some theories of particle physics predict that protons will decay with half-lives of 10 to the 34 power years, eventually dissolving all atomic matter into leptons and photons. If proton decay occurs, it will accelerate the universe's journey toward maximum entropy by eliminating the last vestiges of complex matter. The concept of heat death raises profound questions about the nature of time and causality. In a universe at perfect thermal equilibrium, no events can occur because there are no energy gradients to drive processes. Time becomes meaningless when nothing changes, leading some physicists to speculate that time itself may end with the universe's thermal death. Yet, even in this seemingly hopeless scenario, quantum mechanics may offer escape routes. Random quantum fluctuations in the vacuum could spontaneously create pockets of order within the cosmic equilibrium, potentially giving rise to new universes through quantum tunneling events. These quantum fluctuations might even recreate entire galaxies or civilizations, though the waiting times would be incomprehensibly vast. Some theories suggest that the universe might undergo cyclic behavior, with periods of expansion and contraction driven by the evolution of scalar fields or extra dimensions. In these models, the current universe might be just one cycle in an eternal sequence of cosmic births and deaths, each separated by episodes of heat death and quantum rebirth. The study of heat death and maximum entropy has revealed deep connections between thermodynamics, information theory, and cosmology. The universe's evolution toward equilibrium represents not just the dissipation of energy, but the destruction of information, raising fundamental questions about the nature of physical reality and the possibility of reversing cosmic evolution. Advanced civilizations, if they survive long enough, might develop technologies to extract energy from black hole evaporation or to manipulate vacuum fluctuations. These cosmic engineers could potentially extend the era of complexity far beyond what natural processes would allow, though they too would ultimately face the limitations imposed by thermodynamics. The heat death scenario assumes that dark energy will continue to accelerate cosmic expansion forever. If dark energy evolves, or if modified theories of gravity apply on cosmic scales, the universe's ultimate fate might be different. Some models predict a big rip where dark energy grows strong enough to tear apart atoms, while others suggest cyclic or bouncing cosmologies. As we contemplate this cosmic endpoint from our brief moment in the stellar era, we're witnessing the universe during its most vibrant and creative phase. The galaxies, stars, and complex structures around us represent temporary victories of gravity and nuclear physics over the relentless march toward equilibrium. But even as we face this ultimate cosmic winter, new mysteries continue to emerge from the depths of space and time. Our journey through the Triangulum Galaxy ends where all great explorations must, not with answers, but with deeper questions that stretch the boundaries of human understanding and point toward mysteries we have only begun to imagine. We began with a galaxy that spins impossibly fast, held together by invisible dark matter in defiance of everything we thought we knew about gravity and motion. We witnessed stellar giants that live fast and die young, their violent deaths seeding space with the elements needed for life. We discovered rogue black holes wandering through the darkness, cosmic architects painting nebulae in impossible colors, and ancient stars that preserve the memory of the universe's violent youth. Along the way, we encountered forces and phenomena that challenge our most fundamental assumptions about reality. Dark energy accelerates the expansion of space itself, driving galaxies apart in a cosmic dance that began with quantum fluctuations smaller than atoms. Gravitational waves ripple through the fabric of space-time, carrying messages from collisions so violent they shake the universe itself. Magnetic fields invisible to our senses weave through every corner of the galaxy, creating highways for cosmic rays that race at nearly the speed of light. The galaxy revealed itself to be far more than a collection of stars spinning in space. It is a complex ecosystem where matter and energy flow in cycles that span billions of years. Gas condenses into stars, stars forge heavy elements and explode, their deaths triggering new episodes of stellar birth in an endless dance of creation and destruction. The galaxy breathes, pulsing with rhythms we are only beginning to understand. We discovered that the galaxy does not exist in isolation, but is part of a cosmic web that connects all of space in a network more vast and complex than any structure we can imagine. Dark matter filaments stretch across billions of light years, channeling matter and energy in patterns that echo the quantum fluctuations of the universe's first moment. Yet for every question our journey answered, it raised 10 more. What is dark matter, and why does it outweigh everything we can see by such an enormous margin? What force drives dark energy's acceleration of cosmic expansion? How do black holes really work? And what happens to information that falls beyond their event horizons? Are we alone in this vast cosmic theater, or do other forms of consciousness gaze upon the same stars we study? The search for life in the universe has only intensified as we've learned more about the galaxy's complexity. With hundreds of billions of stars and potentially trillions of planets, the Triangulum Galaxy represents an almost infinite laboratory for the emergence of life. The heavy elements forged in stellar cores provide the building blocks for rocky worlds and complex chemistry. The galaxy's magnetic field may help shield planetary systems from deadly cosmic radiation. But life as we know it requires more than just the right elements and conditions. It needs stable environments, protection from cosmic violence, and perhaps most importantly, time. The galaxy's future collision with Andromeda will disrupt any civilizations that might have emerged in its spiral arms. The gradual fade of stellar evolution will eventually eliminate the energy sources that complex life requires. Yet even as we contemplate these cosmic endings, new possibilities emerge. Perhaps life will learn to harness energy from black hole evaporation or to manipulate the quantum vacuum itself. Perhaps consciousness will find ways to spread throughout the cosmic web, creating networks of intelligence that span galactic distances. Perhaps the heat death of the universe is not an ending but a transformation, a gateway to forms of existence we cannot yet imagine. The tools and techniques that revealed the Triangulum Galaxy's secrets continue to evolve at breathtaking pace. Gravitational wave detectors are opening entirely new windows onto cosmic violence. Space telescopes are peering deeper into space and time than ever before. Computer simulations are revealing how quantum fluctuations grew into galaxies, how dark matter shapes cosmic evolution, and how the universe might evolve over timescales that dwarf human history. Each new discovery seems to make the universe both more comprehensible and more mysterious. We understand how stars work, but stellar nurseries still surprise us with their complexity. We can trace the evolution of galaxies over cosmic time, but dark matter remains as enigmatic as ever. We can detect gravitational waves from black hole mergers, but we still don't know if black holes destroy information or preserve it in forms we haven't discovered. The Triangulum Galaxy has served as our guide through this cosmic mystery tour, but it represents just one galaxy among hundreds of billions in the observable universe. Each galaxy tells its own story, shaped by unique combinations of dark matter, stellar evolution, and cosmic environment. The diversity of galactic forms and behaviors suggests that the universe is far richer and more varied than any single example can reveal. As our cosmic journey ends, we return to the fundamental truth that began our exploration. The universe is under no obligation to make sense to us. It exists according to laws we are still discovering, operating on scales of space and time that stretch human comprehension to its limits. Yet somehow, in this one small corner of one ordinary galaxy, matter has organized itself into forms capable of contemplating the cosmic whole. The greatest mystery of all may be consciousness itself, the emergence of awareness from stellar ashes, and the ability of the universe to know itself through minds like ours. We are the galaxy's way of understanding itself, cosmic archaeologists decoding the history written in starlight and gravitational waves. Our journey through the Triangulum Galaxy concludes, but the adventure of cosmic discovery continues. Each question answered reveals new frontiers to explore, new mysteries to unravel, new wonders to contemplate. In the vast cosmic dark, we have become the light.